Hello friends, welcome back to the tetrahedron chemistry classes. So guys, in today's class I am going to discuss the S block elements, and these S block elements are also known as the alkali metals, and these alkali metals or the S block elements are placed at the extreme left end of the periodic table. So this is their first group, right, which starts from the hydrogen. However, the position of the hydrogen is still actually the confusing. So basically we can start with this lithium and goes up to the francium. This lithium, sodium, potassium, rubidium, cesium and francium, this forms actually the alkali metal group. While the second one, which starts from the beryllium and goes up to the radium, it is your alkali earth metal group, and I will discuss this alkali earth metal in the later classes. Okay, so in today's class I am going to discuss only the alkali metals. So why these S block elements are known as the alkali metals, right? When we dissolve these alkali metals, they form the hydroxides, and that hydroxide solution of these alkali metals is quite alkaline in nature. That's why these elements are known as the alkali metals. Okay, so what are the S block elements? First of all, you can see here, this is actually the first A group which I have shown you here. If I go back, right, so this is your first A group, or simply you can say it is the first group, right? So as you can see here, elements of the first A, the alkali metals, right, and the second A, which are the alkaline earth metals. We will discuss these alkaline earth metals in the subsequent lectures. Okay, so these basically two constitute the S block elements, and their outermost shell electrons are actually present in the s orbital, right? If you want to know, then say if you write the any configuration, for example I am writing the configuration for the lithium. You know the lithium is 3. Okay, so it is what, 1s2, and this is actually the 2s1, and you know the capacity of s orbital is actually to accommodate only 2 electrons. Since only 2 electrons can go into the s orbital, right? So that's why only 2 groups are there for the S block elements, because only 2 electrons can go into the s orbitals. That's why only two S block groups are there. First is your alkali metal, and second is the alkaline earth metal. There is no problem in that. Okay, so this is the way you can say actually how many groups are possible in case of the S block elements, right? Similarly, if you want to know, say if I go back, right, see at the right end you can see here, this is the P block element, right? So here you can see 1, 2, 3, 4, 5, 6. So total 6 groups are there when you talk about the P block elements. And why is it so? Because you know, when you have your P orbital, so P orbital actually maximum can accommodate 6 electrons, right? So if it can accommodate 6 electrons, which gradually fills actually, that's why this actually your P block elements is having the 6 group, right? You can understand the things like that only. So now you can see here, as I already told you, this hydrogen properties are much similar to the alkali earth metals and hence the halogen family. So it's exception case in case of the alkali metals. It should be the alkali metals, not alkaline earth metals, right? Please remember this thing. Okay. Now the next thing is that how where actually they can occur. What should be the occurrence for this, right? So here you can see the occurrence of the group 1 metals. So they are the very reactive one. Please remember this one. This basically this sodium and potassium. Now group is like that, you know. I have already written, like this is lithium, okay, and then sodium, and then potassium. This is your rubidium. This is R, and then your cesium, and then your francium, just like that. Okay. So out of these two, you see, you can see as sodium and potassium, right? This sodium and this potassium, they are actually quite abundant in nature. Their concentration in the nature is very high, right? Their concentration is very high. right? Say somewhere around, if you check your biosphere, so nearly 2.6% of sodium abundance is there, and your potassium is nearly 2.4% abundant in the nature. You should know this thing. Okay, so for the occurrence, you should remember this thing, that your sodium and potassium, if you follow this, right, is if your sodium and your potassium, they are the sixth and the seventh most abundant. So basically this is your sixth most abundant metal, and this potassium is the seventh most abundant element in the earth crust, basically, right? And among all the alkali metals, the less electropositive lithium, right? Please remember, the size of the lithium is very small. Okay, so it is less electropositive, so I can write it here, it is less electropositive. However, I will discuss the anomalous behavior of lithium in pretty much detail, but right now you can understand, out of all the alkali metals, lithium is actually even less electropositive, right? That's why it is found in the nature as silicates. So please remember this point. This is very important for your examination point of view. Lithium silicates, okay, because it is less electropositive, right? When it is less electropositive, due to its smaller size, it forms actually the silicates, okay, while other elements, right, if you talk about these, from sodium up to cesium actually, okay, so they generally form the chlorides, okay, alkali metals, chlorides, okay. Please remember this thing, okay. And your compounds of sodium and potassium are the most abundant compound in the nature, while remaining alkali metals occur in the nature very rarely, okay. However, you know this francium is radioactive. Please remember it is, so it's actually decay by its own, and it is very short lived. And you can see here, this sodium and potassium, I already told you. Lithium and rubidium, they are less abundant. Cesium and francium, more specific, not cesium, but more cesium, though it is having the little of radioactivity, but francium is actually basically a radioactive material, and it decays like that, and its half-life is actually the 21 minutes only. So this is the occurrence which you should know. Now moving to the next slide. Okay, ores. What kind of the ores are present in the nature? This is again a very important question for your competitive examination as well as for your school examination in +2 examination, right? So your spodumene is actually the source of the lithium, which forms which actually occurs in the nature as lithium aluminum silicate. As I already told you, this lithium is very less electropositive, so it forms the silicate, okay. Then second one is the petalite. Petalite is again the lithium silicate, which is the source of the lithium again. And if you go for the source of the sodium, then the common salt or the rock salt, which is the NaCl, the table salt actually, which you commonly use in your house actually, is the main source of the sodium, okay. Then sodium carbonate is there, which is another ore like Na2CO3, again the very important one. Then sodium sulfate, which is also known as the sodium sulfate is Na2SO4. When it is having the water of crystallization, 10 moles of the water of crystallization, then it is known as the Glauber's salt. So this is again a very important question for your examination point of view. What is the formula of the Glauber's salt? The formula of the Glauber's salt is the Na2SO4, right, with 10 water of crystallization. Then cryolide is also there, which is the source of their sodium, and then borax is also there, right, which is again the hydrated form of this borax. 10 water molecules are there. Then sylvine, which is the source of the potassium, that is KCl. Then carnallite, again this is the source of their potassium chloride. It is kind of a double salt, right? It is present along with the magnesium chloride. And then feldspar, with this feldspar is very common, which is the source of the potassium again, and it is again the potassium oxide and the aluminum oxide silicate. It is the double salt. So this is your double salt. The ninth one, which is carnallite one, and 10th one feldspar is the double salt, right? Remaining all are the single salts. Okay, so this is the occurrence, and you should remember the formula and name of these ores, right, of the group 1 metals or the alkali metals. And then if you go for the electronic configuration, guys, electronic configuration is very important. You see the lithium is here, So my suggestion is that you should remember actually your magic numbers, which you have actually started learning in your class 8th or 9th, I think, right? And the magic numbers are 82, 88, 18 and 32, right? If you know the atomic number of the first element of the group in the periodic table, of any group in the periodic table, right? If you know or if you remember the first element of any group of the periodic table, then you can assign the atomic number to the remaining of the group members by using this magic number trick. Okay, so what is the magic number trick? You can see here, this is my lithium, and lithium is 3, and this 3 is greater than 2. So what you can do, after lithium you are having this sodium, and if you add 8 to the sodium, so 3 plus 8, this will give you 11. Now this is 11 your sodium, and again if you add 8 to the 11, then you get the 19, right, which is the atomic number of the potassium. And if you add 18 to the 19, then you will get the 37, which is the atomic number of the rubidium. And if you add another 18 to 37, you will get the atomic number of the cesium. And if you add the 32 to this 55, you will get the 87, which is the atomic number of the francium. So by using this magic number trick, you can remember, or you can remember the atomic number of the remaining elements of the group. So here you can see I have given you the trick also, right? Just like that you can see. However, these slides are not actually prepared by me. I have downloaded this slide from the internet, right? Some Deepa Sharma, the credit goes to some Professor Deepa Sharma. I am using the slide of her actually, okay? But I have also added my own slides, right, and my own literature to this one, right? So if you write the electronic configuration for this 3, so this will give you the 2s1, and this is the configuration of the helium, right? So if you are the beginner here and you don't have the much idea about how to write, so I can write here lithium, which is the atomic number of 3, and I can write 1s2 and 2s1, right? And if you know the helium, actually helium is what? 2. So helium is nothing but 1s2. So if you combined all these two, right, so lithium, the electronic configuration of the lithium can be written as the electronic configuration of the helium, just like that, and 2s1. So what I did actually, I replaced this 1s2 with the helium actually, right? So and it is very important to put this helium into the square bracket actually in order to show the noble gas configuration. Okay, similarly if you go for the sodium, right, this is your sodium. I am writing the electronic configuration of the sodium. Sodium is what? 1s2, 2s2 and 2p6 and the 3s1. Because these are the s block elements, then it is mandatory that the last electron will go into the s orbital. Okay, and now if you check the electronic configuration of your say neon is 10. So it is 1s2, 2s2, 2p6, and here you can write 3s1, just like that. Oh sorry, no, 3s is not there, only 10 electrons are there. Okay, so now if you compare, you see here 1s2, 2s2, 2p6, that means up to this, right? This part is very, very common. See, if you compare these, so this is very common, right? So what I can do, I can write sodium like that, Na11, that is electronic configuration of the neon in the square bracket, it is very important, right? And then you can write 3s1. So this is the electronic configuration of sodium. So on the similar node, you can assign, you can write the electronic configuration of the remaining elements, right? For potassium 19, you can write the argon and 4s1, and for your rubidium, you can write rubidium 37, you can write the your krypton 5 and 5s1, and for cesium 55, you can write the xenon 6s1, and for francium 87, you can write the radon 7s1. So it is, you can see here 2, 3, 4, 5, 6, 7. That means the principal quantum number is changing, and you know whenever you write the electronic configuration, so this actually the prefix 1 and 2, this is actually the principal quantum number. So as you move down the group, the principal quantum number increases. That means the size of the alkali metal increases. So later I will come to the size also, but you should remember whenever we move down the group, the size of the alkali metal increases, right? In case of, not for the alkali, it is not only true for the alkali metals, it is true for your alkaline earth metals and the p block elements as well. Okay, but d block elements are somewhat different. Lots of exceptions are there, right? I'm not going to discuss the d block elements because I have discussed the coordination chemistry in the pretty much detail. I have a playlist actually for the coordination chemistry. If you are watching this video for the first time and you are interested in the coordination chemistry, then you can search in the search bar of the YouTube coordination chemistry by tetrahedron chemistry classes. Then you will find my playlist there. I have uploaded a detailed 40 or 42 lectures in there. Okay, so now next is what? This is the electronic configuration, which is very very important, and you should know about each and everything, how to write the electronic configuration of this. Okay, and then see, if you want to see, if you make the positive ion for this one, Li positive, Na positive, K positive, right? Say I can write like that. Say if I make the Li positive, that means lithium ion. If I can make the sodium ion, then potassium ion, right? And then if I write the rubidium ion, then the cesium ion, and then the francium ion. Okay, if I write like that, so I have removed one of the electron from the outermost shell, right? So what result actually I am getting the noble gas configuration. This is for helium, okay, and this is for neon, and after neon this is your argon, then your krypton, then your xenon, then your radon, right? So this is very very important. So and you know, only one electron is present here, only see, as you can see here, only one electron is present here, so you can remove one electron very easily from them, right? That's why they show, the alkali metal shows the +1 oxidation state. So the relatively very simple chemistry of the alkali metal is probably due to the ease with which their valence electron can be lost from the outermost cell in order to achieve the noble gas configuration. Physical appearance, that means if you look at the crystal structure of these alkali metals, how they look like actually, right? It is something very very important. So first of all, you should know this very important thing. These alkali metals, I am writing here, alkali metals, right? If you cut them with the knife, they are very soft. These alkali metals are very soft. You can cut these alkali metals with the help of the knife or the blade actually, right? So if you can cut them, right, so they actually give you the silvery shiny or silvery shining, right? That means they shine like the silver. So they all are actually, right? So starting from the lithium up to the francium, they all are the silvery white solid. So I can write, and they are so soft that they can be easily be cutted with the help of the knife or the blade or any the sharp things. And why actually these are very very why alkali metals are soft? See, the iron is the very famous metal which is very very hard actually, and other metals like they are also hard, but these alkali metals are very very soft. Okay, and what is the reason of the softness? And the reason of the softness, you can see, if you go back here, you can see only one electron is present. Okay, that means this is the bonding electron, so very less, only one bonding electron is there. So the metallic bond in case of the alkali metal is very very weak, and due to this weak metallic bonding, your alkali metals are soft in nature. If you start from the lithium and go for the sodium and then potassium and so on, right? I can write francium here. Actually softness increases. Okay, so this softness actually increases down the group. As the number of the non-bonding electrons down the group increases, the repulsion between them will actually decrease the cohesive forces. It is increases. So softness increases down the group. This is something very very important. Sodium is 11, and here I am writing here sodium positive. That means you have removed one electron. That means it is having only 10 electrons. So the electronic configuration is like that. if somehow I removed one electron from it, okay, by supplying some amount of the energy to it. So I'll convert this sodium into the sodium ion, and sodium ion is having only 10 positive, 10 electrons only, right? Not positive, 10 electrons only. So here you can see where if you fill the 10 electrons in this sodium ion, then your 3s subshell will vanish. It will go away from there. That means third shell actually, right? The principal quantum number third will vanish from here. That means its size decreases. Okay, you can understand like that in that. See, if you are very beginner here, if you are in junior classes, and say if you are actually your 10th class student or the 9th class student is following this particular lecture, so for them actually, for such students, I can write like that. This is your sodium, say this is sodium nucleus, and this is your first shell, okay, and this is your second shell, okay. So basically this is n equals to principal quantum number 1, and n equals to principal quantum number 2, and n equals to principal quantum number 3. Okay, so I can write the third one here. 8 electrons in this one, 3, 4, 5, 6, 7, 8, and 1 electron is here. And if you remove 1 electron from here, so what will happen? You will end up in the sodium positive. So if you fill the electron again, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So in that case you can clearly see when you remove 1 electron from here, the 3s shell actually vanishes. It goes away actually, or you left with this one. So that's why your cation is smaller than the parent atom. So you should remember this one for the alkali metals especially, or for the alkaline earth metal also, right? Your M positive ion is always smaller in size for M, right? The implication is that your sodium ion will always be bigger than your, so your sodium atom is always be bigger than the sodium ion, and this is also true for the potassium. Potassium is also bigger than your potassium ion, right? You should know this thing, okay? So the atomic or the ionic radii of the alkali metals, they are the largest in the entire periodic table, right? And increases down the group. So please remember, when you go down the group, size increases. Size increases. Size increases means the atomic radii or the ionic radii increases. And why is it so? And answer, you can go for the answer, you can go back. Here you can see the principal quantum number actually increases. Here the principal quantum number is 2, here the principal quantum number is 3. If you keep on going down, then your principal quantum number increases. That means the shell increases. Shell increases means that means you may have one more layer. If you go for the potassium, then again one more layer, so the size increases. So when you goes down the group, the size, whether it is atomic or the ionic radii, it is always increasing. All the alkali metals, they are actually having very low density. So whether your say lithium is there, okay, your sodium is there, your potassium is there, especially I am talking all about these, right? So they are having not only these, all remaining members also, right? Lithium, sodium, potassium, rubidium, cesium, francium, they all are having the very low density, but especially these three, they are less denser than water. The implication is that if you put these metals, if you put these metals into the water, it will not actually go down into the water. It will not actually go to the bottom of the water. It will float over the surface, or these metals will float over the surface of the water. However, it is not recommended. It is not recommended that to add these metals into the water, because it is very dangerous and accident may occur. Go down the group actually, right? So density increase. But again you can see a very important thing is that it is important to put the data here actually for the density. So I am writing here, say and if you go for the data wise, right? So it is not, however, it is not very important for you to remember the data. I am having the data with me, that's why I am putting here. 0.534 is the density of the lithium, and it is at 20 degrees centigrade. Okay, this density, if you change the temperature, the density also changes. You know, the density is the function of the temperature. Okay, and for sodium it is 972 gram per cc, and for potassium it is 0.859 gram per cc, and for cesium 37 it is 1.53 gram per cc, and for cesium it is 1.9 gram per cc. So you can see here it is less denser. If you go here, the density increases. That means, and I already told you the density increases down the group. That means this potassium should have more density than this sodium, right? But this is not happening, right? This is not happening here. And what should be the reason behind this? So this is the very important exceptional question for you. That means potassium has lower density than sodium. Why? Another very important question. So the simple answer is that this is due to the abnormal increase in the volume of the potassium. Okay, so if you write the volume of these two, sodium and potassium, right, atomic volume, molar volume, if you write here, so for sodium it is, the value is 23.68, okay, centimeter cube per mole, and here you can see it is for potassium it is 45.36. so this actually increase is of roughly 22 units. This increase is of roughly 22 units. So this is actually abrupt change in volume, right? And this abrupt, and you know, see, if you write here density equals to mass over volume. So when volume increases, density decreases, right? And this abrupt increase in the volume of the potassium decreases the density of the potassium when compared to the sodium, right? However, here if you go for the, if you compare the molar volume of potassium and rubidium, large, see, increment is there, but that increment is not that heavy or that high, right? That's why this behavior is there. So it is very, very important why potassium has the lower density than the sodium. It is because abnormal increase in the volume of the potassium. And again you can see that due to the presence of the d orbitals, potassium has low density. It is very important to note that when we go down the group, the atomic size as well as the atomic mass both increases. If you go down the group, atomic size as well as the atomic mass both increases, but increase in the atomic mass is more dominant. But in case of the potassium, right, reverse is happening here. In case of the potassium, increment in the volume is too much, is very, very high, right, then the atomic mass. So in that case, in case of the potassium, your atomic volume actually, the size actually the dominant factor, which decreases the density of the potassium. You should remember this very important thing. Okay, now moving to the next slide. See guys, I'm actually giving this, I'm providing this lecture for the students who are studying in the class 11, and it is also equally important for the students who are going to prepare your JEE mains examinations, right, or for your CSIR net or the GATE examinations, right, or in the IIT JAM examinations. Sometimes whatever we study in the JEE, for the JEE preparation, the questions actually comes in the other competitive examinations also. So it is very important for you to focus very carefully, and simultaneously what you can do, you can make your notes. And melting and boiling point decreases down the group. Melting and boiling point decreases down the group. So what, there should be some reason behind this, na? Why the melting and the boiling point decreases down the group. There should be some reason behind this. So what is the reason? So the reason for their low melting in the boiling point is the presence of the weak intermetallic bond, right? Say for example, if you are having K2, right, or say you are having the Na2. So in case of the Na and Na, two Na atoms, okay, so there would be the metallic bond, and you know the only one electron is involved, so this metallic bond is very, very weak, okay, and the weakness of the metallic bond increases when we move down the group. That's why the melting and boiling point also increases, because see, when the size increases, the weakness of the bond also increases according to the size. And you know, if you go for the lithium, sodium, potassium, rubidium, size increases down the group. When size increases, that means the metallic bond strength decreases. That's why the melting and boiling points, both things actually, right? We can correlate the melting or the boiling points, both things with this, right? This is something very, very important. Later I will come to this point also, whether we can form this K2 positive or N2 positive, or your say RB2 positive type of the diatomic actually metals, right? I'll come to this particular point also. Another very important thing. You know what is the modern definition of the metals? That means the elements which can easily remove electrons from them, or electrons from their outermost shell. They are the metal. That means they form the positive ions. And you know, all the alkali metals, if I write the alkali metals with the M, they very readily lose the 1 mole of the electrons to form one positive over there, right? M positive. If you lose the 1 electron from here, okay, it will form the M positive. That means they are metallic in nature, okay. And if they are metallic in nature, and you know the metal are having luster, and in few moments back or few minutes back I already told you, all these metals are what? They are white silvery solid, okay. So there should be the metallic luster in them, okay. So metallic luster. So why this metallic luster is there? This is another very, very important question, very important one, especially for the beginners. It is very, very important, okay. So first of all, you should remember this particular point. Alkali metals are the most electropositive elements in the entire periodic table, and their metallic character increases down the group. Again say, if you go down the group, so metallic nature increases. Why increases metallic nature? As you know, the size, when you move down the group, the size of the element increases. That means there would be less interactions or less attraction between the nucleus and the outermost electron. That means the effective nuclear charge, when you goes down the group, the effective nuclear charge decreases, which sets the outermost electrons rather loosely bound to the nucleus. That means you can very easily remove from them, right? And when you can easily remove the electron from them, that means the metallic nature increases down the group. You should remember this particular point, right? These all are the metals, and thus they are the very good conductors of the heat and the electricity. So it is again very important point. Good they are good. Alkali metals are good conductors of heat and electricity. They also showing the metallic luster, as I already told you. So spelling is little bit wrong here, okay. Metallic luster, and the reason for the metallic luster is quite simple. So what is happening? See, in my lecture of the coordination chemistry, I already told you that the electronic transitions, the concept of the electronic transitions, the colors and all these things, right? But for the beginners, right, why this luster is there? There's something very, very important. You know, all the alkali metals, they possess the metallic luster, and especially when you cut, right? When you cut these alkali metals, so freshly cut metals actually is having the free electrons. See, electrons are already there, but when you cut the metal, then your free electrons are exposed to the environment, right? And they absorb the energy, right? They absorb the energy from the sunlight, and the electronic transition will occur. They move to the higher conduction band, and from them they are falling back, and when they are falling back, they are emitting certain kind of the energy, or that energy or that radiations actually fall on the your visible region, right? And you observe the color or the metallic luster. So basically the presence of the free electrons which undergoes the transitions, and when they fall back into the ground state, they re-emit that particular light which fall on the visible range, and this is the reason for the metallic luster. This is something very, very important. And now the very, very important aspect, and which is the flame coloration. That means when you burn the alkali metal chlorides, right? Say generally first of all, what you do, you convert your metal into the metal chlorides, and then metal chlorides is actually subjected to the flame, and that flame, when these compounds burn, they actually give the color. Okay, this is something very important which you should know. Okay, and what is happening here, you see both groups show the flame coloration. So I am not going for the both group, I am only going for the alkali metals here. The electron present in an atom absorb energy from the flame, and their electrons are excited to the higher energy level, which is the simple concept. When these electrons fall back to the ground state, emit radiations of the different wavelength, and this emitted radiations falls on the visible region, which gives the color to the flame. Again, see guys, please remember, don't get confused. Earlier I have given you the example that why they are lustrous in nature, why metallic luster is there. I have used the same concept of the electronic transitions. When you cut the metal and the electrons absorb fresh light, actually sunlight, and then the electronic transition will occur, and thus they appear as the lustery white or silvery white solid. But here you can see the different colors are there. So color is not for the pure metals, but this color is for the metal halides, alkali metal halides. Please remember this point. Okay, so please remember this point. So here you see here lithium chloride. If you have the lithium chloride, so it is give you the crimson red color, and crimson red, that means you have to identify the color also. So and for NaCl, if you see here, so it is actually shining in yellow color. It is basically golden yellow. Okay, and if you subject your potassium chloride to the flame, if you introduce the potassium chloride to the flame, then you will have the violet color, but that violet color is not very sharp. It is the pale violet in nature. And for rubidium chloride, this color is actually purple. Okay, it is purple. And for cesium chloride, it is the sky blue. Okay, so here I already shown you these colors actually, right? This is something very important. फ्रांशियम की बात इसलिए नहीं करते क्योंकि रेडियो एक्टिव है, उसका कोई फ्लेम कलरेशन नहीं होता है. सो दिस your francium, actually we are not introducing here, so because it is radioactive in nature, it will not give any color to the flame. This is something very important. Please remember, the vapors of the alkali metals, especially in the form of the chlorides, basically imparts the characteristic color to the flame. The reason for this color is that the loosely bound electrons gets excited on heating and jumps to the higher energy level, and from that higher energy levels they fall back into the ground state and they emit the energy of the energy, and that energy falls in the visible region, which gives the characteristic color. Okay, now the next thing is the hydration energy. This is another very important concept, and from this particular concept you may find lots of the question in your competitive examination, right, especially in the competition. Okay, however, the concept of this hydration energy in case of the coordination compound I have explained in my coordination chemistry lecture, but again I am going to repeat that thing here. So first of all, you should know what is actually the hydration energy. Okay, so here see, I don't know, yes, it is written here. Hydration is what? Hydration reaction is the chemical reaction in which a substance combines with the water. The process is known as the hydration. Hydration enthalpy or the hydration energy is the amount of the energy released when 1 mole of the aqueous ions is formed from the gaseous ions. Please remember, or another way of giving the definition of the your hydration enthalpy or the hydration energy is that the heat energy released when new bonds are formed between the ions and the water molecules. That means whatever your ion is present here, say if I can write here, say if M positive ion is there and say water molecule is there, okay, and when they form actually the bond between them, right, so when they form the bond between them, okay, so this is basically this process actually occurs by the release by the release of the energy. That released energy is the hydration energy. That's why I said, I gave the statement that the heat energy released when new bonds are made between the ions and the water molecules. Please remember this particular thing. Very important, and because energy is releasing from the system, that means this hydration enthalpy is always negative. Please remember, it is always negative. Hydration enthalpy is always negative, always negative. However, it is not very important to remember or to learn the values. Okay, so here what is happening, here you can see this is a sodium ion. Okay, and this sodium ion is having the positive charge, and this is your water molecule, right? This water molecule, and you know the water molecule is polar in nature, so you can write positive on the hydrogen, positive on the hydrogen, and 2 negative or 2 delta negative on the oxygen. So this actually negative dipole interacts. See, this will not form any bond. Please, you cannot think like that the sodium ion is going to form a covalent bond or the ionic bond with it. It is only the interaction between the dipoles. Please remember. Okay, and this is get hydrated. Hydrated means water molecules will surround it, right? And during this process, lots of energy is released. That means the reaction is the exothermic, and that released energy is the your hydration energy. So if you want to know this concept of hydration energy in pretty much detail, then you should remember this thing, hydration enthalpy. I am writing here enthalpy. Okay, this is your hydration enthalpy, and that hydration enthalpy is directly proportional to the charge present on the metal. And you know hydration enthalpy is also, it is inversely proportional to the size of the metal. Please remember. And you know when you are discussing the charge, and you know for the alkali metals charge is always positive, because your lithium is positive, your sodium is positive, okay, your potassium is positive, right, your rubidium is positive, your cesium is positive. That means in that case of the alkali metals, you are not comparing this alkali metals with the alkali metal alkaline earth metals. Actually you are not comparing. So if when you are not comparing, and if the charge is same, that means it will not make any difference. So what I can do, I can remove this part from here. So from here you can clearly observe your hydration enthalpy is inversely proportional to the size. That means when the size increases, the hydration enthalpy decreases. That's why if you go down the group, hydration enthalpy, so I can write that hydration enthalpy is delta H hydration, it is decreases. It is decreases. So you should remember this thing, right? That means hydration energy would be higher for this lithium, okay, and it goes on decreasing when you go down the group. This is something very, very important, right? You should remember this particular point. This is something very, very important. So here what you can do, you can write, if you want, then you can write for Li positive hydrogen enthalpy is maximum, and this is for sodium. It follows the same regular pattern actually. Okay, then rubidium, and then here cesium. Francium we cannot include actually. Okay, this is something very, very important. Lithium positive ion has lowest ionic mobility. Lowest ionic mobility among alkali metals. Why it is happening? ऐसा क्यों हो रहा है? ठीक है? So why this lithium? See, it is having the smallest size. That means it is heavily hydrated. Heavily hydrated. That means it is not free to move here and there due to the interaction with the water molecules which surrounds this lithium positive ion. That's why it is having the lowest mobility in the aqueous solution. Please remember this point. If you are going for the mobility of the ions, then the lithium in the aqueous solution especially, then the lithium would be the least mobile. Lithium ion would be the least mobile, and your cesium ion would be the most mobile in the aqueous solution. Okay, I hope you understood the things actually, right? It is also always having the negative value. It is also written here actually. I missed this thing. Okay, next is hydration energy. I have already explained to you all these things. This is the periodic variation, just like that. Size, right? You can see the biggest, it is the minimum hydration energy. See, this thing I have already explained you in the last slide, so there is no point of going or explaining the same thing again and again. Moving further, again this is the value of the hydration enthalpy. It is in the kilojoule per mole, right? So it is going like that, you can see here. Okay, so here you can see the value actually goes on decreasing when you move down the group. This is something very important. Don't get confused like that. It is having the negative value, and this negative value actually is the bigger than minus 1519 actually, right? So if you follow this one, then this will look bigger. It is not like that. Ignore the sign actually. This is always the negative with sign, but there is no mathematical explanation for this one. Okay, you cannot understand in the mathematical way, otherwise you will end up with the confusion that when your cesium is having the higher hydration enthalpy. It is not having the higher hydration enthalpy, only the sign is negative. Okay, next is oxidation and reducing agent. Again a very important thing is there, and that thing is the oxidation and the reducing agent. So it's very easy, you know. It is having very low ionization potential. These alkali metals are having the very low ionization potential, so they can very easily remove one electron from it, so they easily undergo the oxidation. And the species which undergoes the oxidation, they act as the reducing agent. Please remember this particular point. So I am only discussing the alkali metals. You can ignore this alkaline earth metals. So for these alkaline earth metals, what I can do, I can cut it from here. Only focus on this one. Okay, so alkali metals, they readily lose one electron, right? Just like that. So they are very good reducing agents. They are very good reducing agent. Please remember this point. They are very good reducing agent. Okay, and when they generally they forms the special type of the reducing agents also. I'll discuss those things also in a little while, but you should know this thing. Because they have the strong tendency to lose the electrons, s electrons, so they are the very powerful reducing agents. Okay, and if you in the aqueous solution, right, if you go in the aqueous solution, so in the aqueous solution your lithium, right, your lithium is the strong reducing agent as compared to the cesium. This is something very important. Again, this concept is due to the your hydration energy, right? Your hydration energy, you know, high hydration energy for this lithium ion, is hydration energy is very high, and that high hydration energy compensates the ionization potential, high ionization potential energy. That's why this behavior is there. Okay, and if you see, this order is already given here, but you should remember this particular thing, very important. These alkali metals, they are very strong reducing agents. So guys, now let's move on to the chemical properties of the alkali metals. Okay, so in that case, first of all, we are going to look for the chemical property, which is nothing but the reaction with the water or the moisture present in the atmosphere, right? In both ways actually, if you treat these metals with the water, or if they absorb moisture from the water, the reaction actually happens in the same way. So here I have written the metal M, so I have generalized the reaction. Okay, so you can write, instead of this M, you can write your potassium or sodium, etc., all these things. And when these metals reacts with the water, they form the hydroxides, right? And these hydroxides are basic in nature. That's why these metals are also known as the alkali metals. And of course, they will remove the hydrogen gas from here. So it is very important, you know, the certain metals which when you put on the water or on the dilute acid, they remove the hydrogen gas. And here you can see at this particular picture, this is the water, and you have put a certain metal right on it. You can put your sodium or lithium. However, it is not as advisable to do these kinds of the experiments, right? So it is catching fire, and in that case, so all these reactions I have written over there. And the reactivity towards water for these alkali metals, it increases actually down the group. So lithium is the least reactive when it reacts with the water, and your cesium is the most reactive. And lithium hydroxide, as you can see here, it is a very weak base. Okay, but all other hydroxides are highly basic in nature. So this is a very important reaction. So you should remember this particular point. All alkali metals are more reactive, okay, than your hydrogen. Thus they are easily and readily oxidized water, right? And the reaction with water is so exothermic, okay, that the heat generator often ignites the hydrogen gas which is produced, right, which I have shown in this particular picture, okay. So the vigorous nature of the reaction with water for these alkali metals actually increases from lithium to cesium, okay. Lithium is only slowly attacked by the water at room temperature, and though it liberates more energy, it should be remembered that however lithium reacts very slowly but liberates more energy when it reacts with the water, okay. And sodium reacts rather vigorously, and potassium catches fire, okay, when you put the potassium when you put the potassium in the water. And rubidium and cesium reacts very explosively, so that's why these such kind of the reactions cannot be done by the students in the lab. So the fact that the lithium reacts with the water less vigorously, that means less slowly, it is probably due to the very high melting point, okay. Lithium is having the very high melting point, while other alkali metals are having the very low melting points, okay, generally below 373 Kelvin, okay, and they melt due to the heat liberated in their initial reaction with the water, thus exposing more metal surface to further attack actually, okay. The reaction therefore proceeds much more rapidly for the other metals than the lithium, okay, which is very important, while lithium remains almost in the solid state. So these much of thing you should remember when you react the alkali metals with the water. Now moving to the next property, what it says, okay, my next reaction is the reaction with the oxygen. So how actually these reacts with the oxygen, it is again a very important one, and lots of questions in the JEE main examinations actually comes from this particular topic. So here you can see the metal, and I am reacting with this metal with this oxygen, and this bond, right, metal oxide is formed, okay. And then lithium, you can see here I have reacted this I have taken the lithium here, so lithium reacts with this and produce your lithium oxide. It is monooxide, please remember, it is monooxide. So oxygen 2 negative is there, it is simple lithium monooxide. But with the same reaction, when you react sodium with this oxygen, then it will form the sodium peroxide, okay. And if you react your potassium, rubidium and cesium, right, then potassium forms KO2. However, all these things may form the your mixtures of the different kinds of the oxides, the oxides, superoxides and the peroxide. As you can see here, when you have oxide, that means the oxygen is in -2 state. In the peroxide, oxygen is in the -1 oxidation state, and for the superoxide it is in the -1/2 oxidation state. So whatever is written there in this particular slide is not in pretty much detail. So listen carefully what I am going to explain to you, right? It is very important. So please remember these things, okay. Alkali metals, when they are exposed to the air, okay, they readily reacts with the oxygen. See, later I will come to the other components of the air also, because air also contain your oxygen. Along with the oxygen, air also contains your water and carbon dioxide, etc. So the important thing is that when you are having your lithium, okay, so I can write here lithium. Say for example, when you are having a lithium and you are reacting this lithium with the oxygen, right? So it will only form your lithium oxide. It will only form the lithium monoxide, Li2O. If you want to balance this particular reaction, then you can take 2 of lithium and half of your oxygen, right? This would be the only product in case of the lithium, please remember, okay. And if you have, say, sodium, right, say I can write reaction here. If you are having the sodium, okay, and when this sodium is reacting, say, with the oxygen, okay, and the supply of the oxygen is limited, so I can write O here, O2 here, and it is limited. When the supply of the oxygen is limited, then in the limited supply of the oxygen it will form Na2O, that means monoxide. Please remember this thing, okay? And the same thing when you are having the sodium and the supply of the oxygen is in excess, sufficient supply of the oxygen is there, then it will form sodium peroxide. It is something very very important you should know. Na2O2, please remember, okay? And you see your other alkali metals, like if you have potassium in that case, okay? And generally if you treat this potassium with this with this oxygen, it will form your superoxide. Superoxide means like KO2. And similarly if you are having a rubidium Rb and you are reacting with this oxygen, it will largely form the superoxides. However, I am not saying that it will only form the superoxide. You will get the mixture along with this your superoxide. You will also get your say peroxide and the oxide, monoxide also, okay? So these two you can see they are the superoxide, okay? And this is your peroxide, and these are your monoxide, right? So these reactions are very very important, okay? So the formation and the stability of these oxides, whatever you are forming here, they can be explained on the basis of the lattice energy effect. If you know the lattice energy effect, then you will be able to explain why these oxides and the mixture of the oxides is forming. And lithium is always exceptional in that case. You know your lithium, if you are having the lithium positive, it is very very small. Lithium is very small in size, so it can only cater very small size of the oxygen, okay? And that's why it is only forming lithium oxide, monoxide. So it cannot actually cater your other oxides like your say peroxide or the superoxide. So it is something very very important again, okay? And you know the sodium and the rest of the metals are the very large ones, so they can actually stabilize the larger ion also. That's why they are forming your peroxides as well as the superoxides along with the oxide, right? This is again the same slide actually. This is your oxide ion, this is your peroxide ion, this is your superoxide ion. So if you are beginner here, right, and you are starting you have recently started learning inorganic chemistry, then these things are very very important, like oxide, peroxide, superoxide, sulfate, sulfide, sulfide, nitrate, nitrite, nitrite, right? All these ions you should be able to differentiate between them in order to learn the chemistry, right? So whatever the alkali metal is there, right, towards all reagents the reactivity increases down the group. That means from lithium to cesium the reactivity with any reagent reactivity increases, but nitrogen is the exception. In the nitrogen the reactivity order is different. That means cesium to lithium, in that case cesium is more reactive and lithium is less reactive when you take the nitrogen as the reagent. See, you are reacting this with the air actually, okay? And air contains the nitrogen. You know the 78% nitrogen is there. So metal, especially the alkali metal, when reacts with the nitrogen it forms the nitrite, okay? Nitrite means N3, okay? So 6 of the metals reacting with the nitrogen and they are having NM3, okay? That means 2M3N. This is the formula, and you see the if you take the lithium, so 6 equivalents of the lithiums are required with to react with this one equivalent of the nitrogen to form the lithium nitrites, okay? So only lithium forms this nitrite. Please remember, only lithium forms this nitrite. So in that case only nitrogen is written here, but along with the nitrogen lithium can also react with the carbon to form carbides. So what I can do, I can write here lithium when reacts with the nitrogen, okay, it will form nitrite, and lithium when reacts with the carbon it will form carbide. So lithium is the only metal in the group which can react directly with the nitrogen and carbon to form the nitrite and the carbide. So despite having very high ionization energy, lithium is the only alkali metal which reacts directly with the nitrogen and carbon to form the corresponding carbide, nitrites and the carbides. Okay, while other alkali metals do not react directly with the nitrogen or the carbon. So if you are having, say, your sodium and you are reacting directly with the nitrogen, then no reaction would occur. Similarly, if you are having the potassium and you are reacting with the carbon directly, so there would be no reaction. Please remember this point. The lithium is very small in size, right? Lithium, if I take the lithium ion, right, it is very small in size. Or simply the lithium, you can take the example of the lithium only instead of the lithium ion, right? So it is having the very small size. So this is probably due to the fact that the small size of the nitrate and carbon ions coupled with the small size of the lithium ions results in a very high lattice energy. That's why lithium reacts readily with the nitrogen and the carbon. Okay, and thus the heat of formation of these compounds are much higher actually. Okay, and which results in the more stability. And my next property is reaction with the hydrogen. So your alkali metals, when react with the hydrogen, right, so see, that means if you take the mixture of the alkali metal along with the hydrogen and heat them together, it results in the metal hydride, right? Why metal hydride? Because your hydrogen is in negative oxidation state and metal is always positive. Okay, hydrides of such type like MH, like LiH, NaH, KH, right, except Frenchel, while all other hydrides they are generally colorless crystalline ionic solids. Okay, and why they are ionic? Because I already told you this your hydrogen is negatively charged and metal is the positive charge, so it is ionic in nature. Okay, so hydride ion basically present in the crystal lattice. The alkali metal hydrides, all these hydrides actually they possesses the sodium chloride type of the structure. Sodium chloride type of the structure means coordination number would be 6. In case of the NaCl, coordination number of sodium is 6 and coordination number of each chloride is also 6. So these hydrides are also having the same structure as that of the NaCl. Okay, and the ionic character of the bonds in the hydrides increases as the atomic number of the metal increases. That means down the group, if you go down the group, in that case ionic character actually increases because metallic nature also increases down the group. Okay, and the stability also increases in the same manner if you go down the group, right, like that. So stability also increases. So here down the group reactivity increases as I already explained you, and stability also increases in the same manner, and ionic character also increases in the same manner for the alkali metals. Please remember this thing. Okay, but if you can check the data here, what the data is saying actually, your lithium hydride LiH, right, lithium hydride is the most stable. Why? Because it is having it actually dissociates only after your 1273 Kelvin. Here your lithium hydride, which is the most stable one, and it dissociates above 1273 Kelvin. So I can write here lithium hydride dissociates above 1273 Kelvin, while other hydrides dissociates below 773 Kelvin. Okay, so this is I have taken from some standard book actually. Please remember this thing. And the most important thing which you should remember, which is not written here, all these alkali metal hydrides, they are very strong reducing agents. Okay, the alkali metal hydride, they are very strong reducing agents, and their reducing property increases with decrease in the stability. Okay, please remember. So generally in that case you see lithium is very important, right, in organic chemistry generally, right. When you do the organic chemistry, you must have learned about this very famous reducing agent, lithium aluminium hydride. Okay, or lithium borohydride, right. Lithium also forms these things. Okay, and that's why this lithium is very, very important. Okay, so this is all about the properties of the hydride, that means the reaction with the hydrogen. Now let's move on to the next property, what it says. Okay, the most important one, by far this is the most important one, I can write here, and in your CSIR net examination, in IIT JAM, or in the GATE examination, you may have the question from this particular topic also, the reaction with the ammonia or the liquid ammonia. Okay, ammonia, that means you can put these metals in the ammonia also, right? And the reaction is very, very important. So what is written here, you see, all the alkali metals dissolved in the liquid ammonia giving deep blue solutions. Initially it is not deep blue, actually initially it is light blue when the concentration of the ammonia is very dilute, right? When it is when in the dilute ammonia the color is the actual light blue, and when you increase the concentration of the ammonia, that means if you keep on adding more and more ammonia, then the color changes from light blue to deep blue solutions. Okay, so here it is written, when dilute due to the presence of the ammoniated solvated electrons in the solution. So this is not actually right, this is not the exact correct explanation, right? I'm sorry for this one, because as I already told you a few minutes back, these slides are downloaded slides, not very up to the mark, but please listen carefully what I am saying, because this slide is not the up to the mark. So first of all, you should remember this thing. When you heat this alkali metal, right, in the ammonia gas, somewhere around the 400 degree centigrade, right, and you have to add little of your iron, then the first reaction is the formation of the metal amides. Okay, this is the first property. In case of the first property, what you can do, say for example you are having the sodium, okay, and you are having the ammonia gas. So first I am taking the example of the ammonia gas, okay, and in presence of little of the iron fillings, and temperature is somewhere around 400 degree centigrade. So it end up with the sodamide, NaNH2. But this is in case of the ammonia gas. See this reaction, your cesium is the most reactive, followed by the rubidium, and then your potassium is there, and then your sodium and lithium is least reactive. Right? This particular reaction is not there in this particular slide. That's why I have written the reaction here. However, the important reaction is there in the slide actually. Okay, now I am discussing the liquid ammonia. So all the alkali metals, they are soluble in the liquid ammonia, and they give you the solution which is highly conductive and blue in color. Sodium metal, right? I am writing here. See, you are having the sodium metal, and in case of the sodium metal, if you treat this sodium, if you put this sodium metal into the ammonia, like here NH3, right? If you put this into the NH3, then it will give you the things like that. First is M, NH3, so I am writing X here, okay, and I am putting positive over there, that means it is in +1 oxidation state. So this is actually this particular complex. And next is your ammoniated electron. See, NH3 and Y is here. Since this is electron, so I can put negative here. So these two species generally formed. And in that case, this is your cation, this is your anion, and they have the different functions. Okay, now you can see when what I told you, in dilute cases, dilute solution means less ammonia. When you put any metal like sodium metal, it will give you the light blue color. So what should be the reason behind this? For the reason is this ammoniated electron. So the color of the solution is due to the ammoniated electron. But if you increase the concentration, right, if you keep on adding ammonia to it, okay, then this color would be deep blue. So first of all, you should remember all these dilute solutions, right, only one electron is there. You can see here one electron is there. So if the solution is dilute, then it is paramagnetic in nature. Please remember, okay. Why? Because this free electron is there. Now if you keep on adding ammonia and make the solution more concentrated one, what will happen? The electrons gets combined and they form a pair. So this deep blue is actually diamagnetic. It is diamagnetic, and this one is the paramagnetic. So we have discussed the magnetic nature. So why I have introduced the magnetic behavior here, because it is very important. You should know that in the dilute solution the free electron is there, single electron is there, which gives the paramagnetic nature to this particular solution. When you keep on adding ammonia, the electrons get paired, and the color also changes from light blue to deep blue, and the solution becomes your diamagnetic. So I can write color, and I can write electrical conductivity. Color is due to the ammoniated electron, and conductivity is largely due to this cation along with ammoniated electron also. Both are the contributing factors. You must be wondering that why I am not actually giving the value of the x and y, which I am using frequently right here in the equation. So values of x and y, it will depend upon the solvation by the ammonia, right? It varies actually on the concentration. Okay, so this is again a very important one. And the solutions which are these solutions are strong reducing agents. Why reducing agents? Because they are having electron, right? And these electrons can reduce any other salts, reduce your metal halides, right? Metal halides to metals. Say for example you are having the metal halides and you are reacting this, then it will reduce to the metals. Similarly, if you are having your nitrogen oxide like laughing gas, so it will give you the nitrogen, okay, because it is the reducing agent. Similarly, if you are having say oxygen, okay, and you are using the same reagent, then it will give you this peroxide, okay. And then you may also think about this O2 negative superoxides or the peroxides also. So this aspect is very important. Birk reduction is there, so I'm not going to discuss the Birk reduction. Actually in the Birk reduction we use the same combination, the liquid ammonia and the alkali metal. It is a very famous reaction. If you are not aware about this particular reaction, you can go through the description box. I am giving you the link of the Birk reduction. I have also made a video on the Birk reduction. You can go there and see how it is acting. Okay, so generally these alkali metals they replace hydrogen from the oxidizing acids. So this is my next property, that means the reaction with the acids. And you know the acids are of the two types. First is the oxidizing acids, and second is the non-oxidizing acids, non-oxidizing, right? These two kinds of the acids are there. And your non-oxidizing acids are generally dilute HCl or your dilute H2SO4, and your oxidizing agents are the concentrated one, concentrated HCl, concentrated H2SO4, and your HNO3. HNO3 actually could be anything. It could be a dilute or it could be the concentrated one. In the both ways the reaction goes well actually, right? So how they can react? For example, you are having the H2SO4, okay, the H2SO4, and you are reacting with the metal. Say you are reacting with this one. So what it will form? It will form, of course, Na2SO4, sodium sulfate, and you will have the H2S gas, right? And then the water molecule. These reagents would be there. If you want to balance this particular reaction, then you will need 5 of H2SO4, 8 of Na, that means 4 of sodium sulfate, H2S is there, and of course 4 of water molecule. Okay, so here 4 and 1. Okay, so this is the balanced reaction, right? This is important. Now suppose you are having your HNO3, you are reacting this with HNO3, and for example it is concentrated one. Okay, for concentrated acid you are reacting this with sodium. Again your 8 equivalents required and 10 of this required, because it is monobasic acid, right? So the value would be the double that of the dibasic acid, that is H2S. So it will form the metal nitrate. 8 of so I can write Na instead of this Na. So here this is 8 of NaNO3 plus your N2O and your 5H2O. Okay, So this is your laughing gas, please remember. And suppose your acid HNO3 is dilute, not concentrated one, that means it is having the water, so you will require 9 equivalent of this one, and of course 8 of your sodium, right? So it will not make any difference whether you take sodium or potassium or rubidium or cesium, the reaction always goes like that, okay? NO3, and then you are having the ammonia, and then your 3H2O. Okay, so these are the reactions. So what important observation you can make from here: whenever your oxidizing acids are there, right? These all are your oxidizing acids, right? Concentrated H2SO4, HNO3, whether it is dilute or concentrated, it is not liberating hydrogen from the acids, but it is forming your hydrogen sulfide H2S gas. It is forming laughing gas, it is forming ammonia gas. So 3 gaseous products are formed. But if you put the metal in the non-oxidizing acids like dilute H2SO4 or dilute HCl, as you have seen earlier, they will quickly remove hydrogen gas from here, H2, right? You can write here nature of nitrates. Okay, so first of all, in the last slide, if I go back, you see I have formed these nitrates, right? NaNO3 and NaNO3. So I am discussing the properties of these. So nitrates are basically your MnO3. It could be your LiNO3, it could be your NaNO3, it could be your KNO3. So their properties are what? They are colorless and water soluble also. And they are ionic in nature. Okay. And they do not actually hydrolyze. See, and a very important property is there. However, these nitrates of alkali metals do not hydrolyze, but they decompose on heating. Please remember all the nitrates except your lithium nitrate. So what I can write here, exception. I can write exception here, and this is your lithium nitrate, which I'll discuss in a little while. While see other nitrates, like if you are having the NaNO3, sodium nitrate, if you heat it, it will decompose to give you sodium nitrite, NaNO2, along with the oxygen. And same is true with the potassium nitrate also, KNO3. Okay, potassium nitrite with the oxygen. This is on heating. So whether you take the sodium, potassium, rubidium or cesium nitrate, they dissociate to give you the nitrites. So basically it is sodium nitrite. Okay, the spelling is NiTrite because it is NO2 negative. Don't write nitride, it is nitrite, not nitride. Okay, while this lithium nitrate is the exception. If you heat this lithium nitrate, okay, then it will give you the lithium oxide, Li2O, and 2 of the NO2 will remove from here along with the half of oxygen. So this is something very, very important. So why actually this happens actually? So basically it is due to the more polarizing power of the lithium ion. Your lithium ion, right, Li positive, it is very small, so its polarizing power is very, very high. Polarizing power is high, so it will polarize oxygen to form the lithium oxide. Okay, because the oxide is also a very small ion. Okay, so they actually interact to form the lithium oxide. So if you don't know about the polarization and polarizability and the Fajans rule, again you can check the description box. I am giving the link of the Fajans rules. Okay, I have also formed the sulfates, right? You see here nitrates. I have discussed the properties of the nitrates. Now I have also formed the sulfates, so it is very important to see the properties of the sulfates as well. Again a very, very important one. And the sulfates of kind M2SO4, Na2SO4, K2SO4, etc. These are very common. Okay, these sulfates are basically water soluble. But again you see here lithium sulfate, Li2SO4. It is also water soluble, but its solubility decreases on increasing the temperature. Why? because the reaction is the exothermic in nature. See, if you put H2O, if you put this into the H2O, and then it will form the solution, and it will liberate some heat. And since the reaction is the exothermic reaction, okay, and due to this exothermic reaction, if you increase the temperature of the system further, that means it will not, if it is exothermic reaction, that means it is liberating heat. The system is not required heat. If you supply the temperature, if you heat it again, then the solubility of the lithium sulfate decreases. However, in some of the textbook, you will also find that the lithium sulfate is not soluble while other sulfates are soluble. It is not true. It is less soluble, but solubility further decreases when you heat the system. Okay, this is something again important point to remember. Okay, and another very important thing is that, see, these alkali metal sulfates, if you have say K2SO4, if you have K2SO4, it is a very such sulfates are having very strong tendency to form the double salts. They form the double salts. Okay, and they can form the double salts along with the with your say iron. They can form the double salt with the aluminium. Okay, and you may take the chromium also, right? All double salts can form. A very famous double salt, you know, K2SO4, Al2SO4 whole thrice, dot 24 H2O. This is potass alum, and it is a double salt. Okay, and this 24 order of crystallization is there, and many other double salts you can also form. But you see, lithium actually will not, see, it is forming alum. This potassium is forming alum, sodium can form alum, but lithium is not known to form the alum. So I can write this in the form of the question: why lithium does not form alum like potassium? Okay, again, you know, this lithium is an exception, and Li positive is very small in size. Okay, Li, it is very small, and to form a lattice of the double salt, so this lithium is very small, and due to the extremely small size of the lithium, it is not able to form a stable complex required by the double salts, or say the alum actually. Okay, so while you see potassium is larger in size, so it can stabilize this particular crystal lattice, but lithium, due to the small size, cannot stabilize this lattice. That's why the alum of the lithiums are not known. So these alkali metals are known to form the halides. Okay, so halides of kind Mx, and if you take the Mx, that means you are having the NaCl, you are having the KCl. Okay, and then you are having the other halides as well, etc. So these alkali metals readily form halides with the when reacting with the halogen. And if you know the coordination number of this NaCl, right? So sodium 6 and chloride is also 6. So 6:6. That means 1:1 ratio is there, and this whether it is sodium chloride or the potassium chloride, they will have this particular ratio. But exception is there. Say if you are having after potassium, rubidium, and then the cesium, say you are having the cesium chloride. Not only cesium chloride, if you are having the cesium bromide or the cesium iodide, whatever the halide is there, okay, in that case the coordination number would be different. The ratio would be 8:8. So you should remember this point. For NaCl, for alkali metal, among alkali metal halides, NaCl is having the coordination number of 6 of your sodium as well as the chloride. Okay, while in case of the cesium halides like cesium chloride, bromide, and the iodide, this coordination number is 8:8. Right? And why it is actually happening in that case? It is due to the more favorable lattice energy. In case of, see, if you have the lithium, theoretically it says that the lithium is having the coordination number is 4:4. If you have the lithium chloride, 4:4. but lithium can also form this particular ratio, 6:6. So guys, my next important compound of the alkali metal is are the alkali metal carbonates. So I can write the alkali metal carbonates. Basically they are the oxysalts. Oxysalts means the sodium, the salts which contains the oxygen. You know the alkali metal is electropositive, it can form the Na positive, and it can react with the carbonate to form the compounds like alkali metal carbonates like Li2CO3 I can write here, and then I can write Na2CO3, which is again like that, and then I can write K2CO3, etc. Okay, so these are the carbonates, these are the oxysalts. You may think of your bicarbonates as well. So these all are actually very stable. Please remember, these oxysalts are very stable. What is the meaning of the stability? The meaning of the stability is nothing. If you have the sodium carbonate, okay, and if we heat it, no reaction at all, okay. But if you take your lithium carbonate, Li2CO3, if we heat it, then it will break into the lithium oxide along with the carbon dioxide. So this reaction which I have written here, it is only possible in case of the lithium carbonate, while this reaction is not possible for the other carbonates. That means your lithium carbonate is the least stable and it is decomposing readily on heating. So why actually it is happening in that case? The only reason is that this cation, this Li positive, if I write in the form of, again you see the reason is same but explanation is different, but reason generally is same. So Li positive is there, okay, and this is small in size, so its polarizing power is very high, okay, and it can actually form the salts with the small anions, and you know the oxygen is a small anion, so this is rather more stable than this particular one. That's why it facilitates this kind of the decomposition. Okay, so whatever the gain in the lattice energy would happen, right, due to this substitution of the oxide ion from your carbonate ion, it enables the decomposition. The driving force of the decomposition is what? Gain in the lattice energy resulting for the substitution of the smaller oxide ion from the larger your carbonate ion. This is the reason actually. Bicarbonate, if you take the example of the bicarbonates, right, so bicarbonates like sodium bicarbonate, CO3, so all the bicarbonates of the alkali metals, again they can be obtained in the solid forms, so it could be it is solid. And similarly, if you have the potassium bicarbonate, it is also solid in nature, okay, but lithium is actually not like that. And all the carbonates or bicarbonate, they are water soluble, but lithium carbonate would not dissolve readily in the water. It would be less stable, or you can say the sparingly soluble. Anomalous behavior of the lithium. First of all, you know, very small in size, polarizing power is very high, that means charge by radius ratio, okay, and its ionization enthalpy is very high. That's why ionization enthalpy is very high. That's why it is formed the covalent compounds but not the ionic compounds. Electropositivity is very low. That means it is less metallic when compared to the sodium, potassium and others. Okay, this thing. Now next, okay, now the reactions you can see in water. Lithium is reacting with the water to form this solution LiOH, which is actually the weak base, while other metal hydroxides like sodium hydroxide, potassium hydroxides, they are the strong base. Please remember, this is weak base while rest are the strong base. Now if you react this with the air, lithium is forming only this particular oxide which I have explained, while other can form the oxides, superoxides or the peroxides. But you know the air, in the air your nitrogen is also present, so lithium can react with the with the nitrogen directly to form the nitride as well as the carbide, as I have explained in my last slide, and it can react with the hydrogen to form the hydrides. But lithium hydride is quite a stable one. Why? Because this lithium is very small in size and this hydride is very small in size, so it forms a very strong lattice. That's why it is stable. While you know the other metals are little bigger in size when compared to the size of the hydride, so their actually other metal hydrides are less stable. Then along with the halogens, you can see it forms the soluble metal halides, but lithium fluoride is insoluble while other are soluble, right? Now next, right, see this I have explained, lithium weak base, this I have explained. And least reactive, strong reducing, see lithium, the air, lithium monoxide, lithium nitride, I have already told you. Lithium hydride most stable. So all these things I have covered. Lithium carbonate I have covered, lithium fluoride, and then the lithium phosphate. They all are the sparingly soluble. That means they are not readily soluble in the water. Next is lithium melting point and boiling point, right? Very high. It is a hard metal. Due to the hardness, metallic crystalline structure, high lattice energy. Okay. So, and lithium chloride is deliquescent. So now see guys, it is something very, very important. Hygroscopic, deliquescent. What is the difference between hygroscopic and deliquescent? It is again very, very important, and students should know about this thing. See, hygroscopic basically is the ability to absorb moisture, from atmosphere, and deliquescent means it will form liquid with the water. That is the deliquescent nature. Substances that dissolve in the water. How your substance is the hygroscopic, which is decide the deliquescent nature. So this thing you should know. So this LiCl is your deliquescent in nature. That means it will dissolve in the water to form. It will absorb the moisture and gets completely dissolved and form a solution. While your sodium chloride NaCl is there, it is hygroscopic. It will absorb the moisture, but it will never form the solution. Okay. And why this happens? Due to the very high hydration enthalpy. And then you see lithium nitrate, I have discussed, the decomposition is like that, while other will form like that. Okay, this I have discussed. And lithium carbonate I have discussed, it will give you the this lithium oxide. I have explained this one. For lithium bicarbonate, it will not obtain in the solid form, while other alkali metals would be obtained in the solid form. It will form your lithium imide. Okay, or while rest will form the amides. So this is again very important, which I have missed actually. Lithium forms the lithium imide, okay, while other forms the amides. And after that, again a very important aspect, that is the diagonal relationship. This lithium is there and magnesium is diagonally placed to this particular lithium. So that means the properties of the magnesium would be similar to the lithium. They have the similar properties. So the diagonal relationship is said to exist between the certain pairs of diagonally adjacent elements in the second and the third periods of the periodic table. So what is the similarity? Reason? Similarity in the ionic sizes and similarity in the radius ratio effect, charge radius effect. Atomic radii, if you compare, lithium is 152, magnesium is 160, they are very, very similar. If you take the ionic radii, again 76 and 72, very similar. If you take the polarizing power 1.7 and 3.9, it is however actually difference is quite high, right? And electronegativities are quite similar. Points of similarity between them. Lithium hydroxide is weak, of course magnesium hydroxide is also weak. Lithium forms the lithium nitride, magnesium also forms the magnesium nitride. Okay, and you should know this thing, right? Magnesium is what? 2 positive, and your N is 3 negative. I can write like that. So it will give you the Mg3 N2 like that. Okay, this will come here and this will go there. Okay, and you see lithium is hard here, even magnesium is hard. LiCl is deliquescent, magnesium chloride is also deliquescent. So it is dihydrated, it is octahydrated. Lithium carbonate decomposes, as I already told you. Magnesium carbonate also decomposes. Lithium hydrogen carbonate, bicarbonate, cannot be obtained in the solid form. Magnesium bicarbonate cannot be obtained in the solid form. So these are the similarities. These are the crown ethers. This is 12 crown 4 if you number it, right? So I can write like that. Say this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this 12 is for the all total atoms. 4 stands for the oxygen because 4 oxygens are here. 1, 2, 3, 4. It is 12 crown 4. Okay. Now if you see this one, so 15 is there. You can do by your own. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So it is 15 crown 5 because 5 oxygens are there. 1, 2, 3, 4, 5. So these are the crown. Similarly, you can do for this 18 crown 6 also. And you know this lithium ion, actually lithium ion can only be fit or the sit into this particular cavity, and that's why it forms the compound with this one. Here you see the lithium is fitted here, and then you see the potassium will fit here, and your cesium will fit here. 18 crown 6. Okay, so these are the alkali metal compounds, the important one. Along with this crown ethers, the cryptane compounds are also there, but I am not discussing the cryptane compounds here. Okay, I'll discuss this thing in the later stages. So what is the bioinorganic chemistry? For bioinorganic chemistry, you know the sodium and potassium, these ions are very, very important for us. So not only the sodium and the potassium, but alkaline along with this alkali metals, alkaline earth metals like magnesium and calcium are equally important for us. But in general, you should know your sodium ion, actually it is extracellular fluid. Extracellular fluid means if you see here, sodium is outside the cell here, extracellular ion, while your potassium is the intracellular ion. It is present in the inside the cell actually, and your potassium is found in the intracellular fluids, that means inside this, like in the cytoplasm. And see, substantial amount of sodium and potassiums are required, okay, to prevent the different kinds of the diseases. So see, whenever your sodium is present inside this intracellular fluid, it will be pushed out to the extracellular and it will require some energy. It will act as the potassium pump. So in the biological system, sodium potassium pumps are also there. So the biological machines, you should remember this particular point, the biological machines that are responsible for the selective transport of the ions, metal ions, okay, they are basically the very complex assemblies of the proteins, and they are known as the ion pumps, okay, sodium pumps or the potassium pumps. And these ion pumps actually recognize and discriminate between the metal ions in the same way as I have discussed for the crown ethers. That means in case of the crown ethers, in certain size where sodium is fitting, in certain size cesium is fitting. In the same way in the ion pumps also, right, in the proteins where certain ions can go in and out. And if some defects are there in the ion pumps, then serious diseases may result. Like for example, chloride ion is responsible for the kind of the disease. However, I am not discussing the anion here, but you should know about the other things also. Like say what I have written here, you see, hypertension. So in many cases, your hypertension, your high blood pressure, right, they are thought to be the defect in the sodium uptake or the excretion. That means you are say if a sodium intake is very, very high and excretion is low, then you may have such kind of the problems. If too much of the sodium is absorbed by your body from the diet and very little of the sodium is excreted, then what will happen? Water diffuses from the tissues into the blood and blood gets diluted. Thereby this decreases the osmotic pressure in the circulatory system, and this will increase the blood pressure, okay, and it may rupture the arteries, right, and it may also result in the brain problem. And you know, the patients which are suffering from the hypertension, low sodium diets that use the NaCl substitutes like KCl are often prescribed. If hypertension is there, then you should take KCl instead of the NaCl. However, the taste of the KCl is same as the NaCl, but you will not require the NaCl when you have the hypertension. Okay, and one more thing, if you see, the potassium ion basically is not readily taken up by the body, so only limited amount would be present inside the system. Basically, this is the method to control the hypertension. However, it is debatable. So guys, in today's class I am going to discuss S block elements, and in S block elements today we will discuss alkali earth metals. Okay, in my last lecture I have explained the alkali metals, where that is the group 1 elements. Okay, if you haven't seen that particular lecture, kindly go through the description box. I have given you the link of the group 1 metals, lectures of the group 1 metals. You can learn the group 1 metal also. Okay, and now I'm going to start this group 2 metals, which is technically known as the alkaline earth metals. Okay, so here you can see I have written the group 2, and here I have written the metals. Why they are metals? Because they are electropositive. They have the tendency to lose the electron to form the positive ions. Okay, and I have written here the less reactive, but please remember these alkaline earth metals are less reactive compared to the alkali metals. Okay, so if I want to complete this, so here you can write your lithium, sodium, potassium, and so on. Please remember this particular point. These alkali earth metals are less reactive only compared to the alkali metals, and whatever the properties you have seen for your alkali metals in my last lecture, all those properties will also be given by the alkaline earth metals. Okay, they are very reactive, of course, but less reactive than the your alkali metals. That is the group 1 elements, right? This thing is very important to understand. Now you can see here, if I go their occurrence, so first of all, you see here I have written beryllium, magnesium, calcium, strontium, barium, and radium. These are the elements, and I have written their occurrence in the earth crust. So your calcium is actually the 5th most abundant element in the earth crust, and your magnesium is 6th, not 6th actually. It is error in this particular slide. Please remember, it is not 6, but your magnesium is 8th most abundant element in the earth crust. Okay, and strontium and barium, their occurrence is quite lower, while you can find beryllium rarely in the earth crust, right? And that's why it is not included in the true alkali earth metals. Later I will come to that particular important questions also. And your radium is the rarest, and which is the radioactive also. Please remember these things points. And if you want to know their trivial or the older name, then you can go through the textbook, right? Like your magnesium is known as the magnesia, right? And this beryllium is known as the beryllia, right? And then this is strontia, right? And this barium is the baryta, right? All these things you should know. Okay, and now if you want to know the electronic configuration, so I have already told you in my last lecture, you in chemistry basically, right? I am talking about the chemistry, not the mathematics. Okay, in chemistry, wherever we are talking about the magic numbers, these magic numbers are 2, 8, 8, 18, 18, 32. What is the use of these magic numbers? I have also explained in my last lecture of the alkali metals, but if you are new here and watching video for the first time, I am explaining the things again, right? You have to remember these, or you have to learn these magic numbers. And in the periodic table, if you know the atomic number of any first element, then you can get the atomic number of remaining elements present in the particular group. For example, beryllium is 4, and you know this 4 is greater than 2. So you will start from here. If you add 8 to this 4, it will give you the 12. So 12 will be the atomic number of the magnesium. And again, if you add another 8 to the 12, then it will give you the 20, which is the atomic number of the calcium. If you add 18 to the 20, right, that means you will get the atomic number of the strontium, that is 38. If you add another 18 to the 38, then you will get the 56, which is the atomic number of the barium. And then if you add 32 to the 56, then you will get the 88, which is the atomic number of the radium. Okay, and if you want to write the electronic configuration of them, then you can see for 4 you can write 1s2 2s2. This is the electronic configuration of the beryllium, and you know this 1s2 is the electronic configuration of the noble gas, and that noble gas is the helium. So instead of writing 1s2, what I can do, I can write that helium in the square bracket, which shows the electronic configuration of the helium, and remaining part is the 2s2, which I have written here. Similarly, if you go for the electronic configuration of the magnesium, then you can write 1s2 2s2 2p6 and 3s2. And if you know, see, if you check this this part actually up to from 1s to 2p, so 2 plus 4, 4 plus 6, that is 10, right? That means total 10 electrons are here. So this is actually the electronic configuration of the neon. So what I can do, I can write neon here, and then I can write the 3s2, which is the which are the 2 electrons present in the 3s orbital. So in the same way, if you continue to write the electronic configurations of these, then after neon you are having the argon, so you can put this argon in the square bracket, and after that you will write the 4s2 here, and after argon you are having your krypton. Okay, so this is the electronic configuration of the krypton, and this is 5s2, and then you come to this one, xenon, electronic configuration of the xenon, and then 6s2, right? And then you are having the radon, and then you can write 7s2. So your you can see here your last electrons actually are entering in the s orbital. This is the region. This group 2 is also included in the group 2 elements. Okay, so this is the use of the your you can say the magic numbers. Okay, and now moving to the next thing. The next thing is, see, before moving to the next thing, I want to give you an important information about these compounds also. You know this magnesium is very important, which is found in the various biological systems, and its hydroxide is used in the antacids, right? So okay, and why? Because from the intestines this magnesium hydroxide absorbs water, and which loosens the stools actually, right? So it is occasionally used for the removal of the constipation, magnesium hydroxide. But please remember, compounds of beryllium and compounds of barium, they are very toxic, and you have to be very carefully while dealing with the compounds of these two, barium and the beryllium. They are very toxic. Like, see, beryllium, if you go for the toxicity of the beryllium, see, beryllium is basically a skin irritant, okay, and it can result dermatitis, and sometimes it is all, see, if inhale in certain quantities, right, then it can provide a person acute pneumonitis, right, and chronic pulmonary diseases can also be caused by the beryllium poisoning. Similarly, your barium compounds, right, these barium compounds are also very toxic, which actually results in the watery diarrhea, right, vomiting. It can induce the sensation of the vomiting, right, abdominal pain it can give. So please, while this is something very important, while magnesium hydroxide is actually used in the medicines as antacids, while the compounds of the beryllium and the bariums are quite toxic, you should know these things. Okay, now moving to the next slide. Okay, now these are the important questions, especially for the beginners. Why the group 2 metals are called the alkaline earth metals? So I have summarized the 2 points here. You can see here. See, if you dissolve the metal oxides, right, they are hydroxides, and how we can form the hydroxides of this? It's quite simple. If you have, say, magnesium oxide, right, and if you dissolve this magnesium oxide into the water, it will give you the magnesium hydroxide, and this reaction is true for the remaining of the members also. Okay, magnesium hydroxides. So basically their hydroxides are alkaline in nature. That's why the alkaline word is there. Examples are the magnesium hydroxide, calcium hydroxide, strontium, and the barium hydroxide, etc. and their oxides, right? I have written in case of magnesium oxide is the example, like their oxides like MgO, CaO, they are earthen in nature. That means they found in the earth crust. And earlier chemist, actually older chemist, or you can say the alchemist, what they understand, why they actually given the name this earth, actually because they are very high melting. These oxides are very high melting. So whatever the temperature available for the in the past for the older chemist, right, at that particular temperature these compounds are actually not melting, right? And which the things which are not melting, the scientists call them as the earthen. That's why this word earth is there. And since they can remove electrons to form the electropositive ions, that's why metal is also there, and it completes the name alkaline earth metals. This is something very important which you should remember, guys. Very important question, right? Now what is the next question? What it says, why beryllium is not a true alkaline earth metals? Now it is quite easy. I have given you the 2 points in the above question, like this is the point 1, this is the point 2. So you know the oxides and hydroxides of beryllium, if you make the hydroxides of the beryllium and oxides of the beryllium, they are actually not at all alkaline. They are amphoteric in nature. Okay, they are amphoteric in nature. And since they are amphoteric in nature, they are not actually alkaline. So they are not alkaline, so we cannot include the compounds of the beryllium in the alkaline earth metal. So in a true sense, right? However, it is very rare to find this particular explanation in the textbook. In many of the textbooks, in certain standard textbook you can find. So for this particular region, that is the it cannot fulfill the point number 1. So their hydroxides are or oxides are not alkaline, but they are amphoteric. So that's why they are not alkaline earth metals. However, they fulfill the second criteria. They are earthen, actually high melting. Okay. So this is something, another very important point which you should remember. Now moving to the next slide, what it says. Okay, their occurrence. How you can find these elements in the nature. See, magnesite is the ore, okay, which is the ore of the magnesium carbonate, okay, and magnesium is abundant in the nature, if you know, okay. And dolomite is another very important ore from which you can extract your magnesium. However, calcium is there, but from this you can extract magnesium only, okay. Then in the abundant amount rather, okay. And then you are having the carnallite. Carnallite is a kind of the double salt, like earlier you can see that dolomite is the double salt. Your carnallite is also the double salt, which is nothing but the potassium chloride and the magnesium chloride double salts, and it is hexahydrated. Please remember, water of hydration is 6 here. So from here again you can collect your, or you can extract your magnesium. Then Epsom salts are very common. Epsomite is the name. Magnesium sulfate, heptahydrate. And then you are having the limestone, which is the source of the calcium. Marble, chalk, calcite, everything, right? Lots of things are there to extract the calcium. And then anhydrite is again there, which is nothing but the calcium sulfate. And gypsum is very important compound in the cement industry, which is the source of the calcium. And there's fluorspar. You might have heard about the fluorspar, which is commonly used for the extraction of the calcium, okay. And then you are hydroxyapatite and the phosphorite. So these are the abundant ones. That's why their ores are given here, while others are rare actually. Okay, so my next slide is the atomic size or the ionic size. So however, I have written only the atomic size here, but whatever I will explain for the atomic size, that will true also for the your ionic radii. Okay, so you can see here the group 2 elements. See, these are the group 1 elements: lithium, sodium, potassium, and it goes up to the rubidium. And these are the group 2 metals, that is the alkaline earth metals. It starts from the beryllium, and the group goes like that: magnesium, calcium, strontium, barium, and the radium. And if you compare the size, you know the down the group size increases. So definitely the down the group size increases for the alkali metals as well as for the alkaline earth metals. That's why you can see here this circle is smaller, this circle is quite bigger, this is another relatively bigger, and this is the biggest one. This shows the increase in the size, okay. And now if you compare, see, they are the bigger in the size. If you move across the period, you know, in the across the period size decreases, which I have written here, okay. and down the group size increases. That means they should have the smaller size when compared to the your alkali metals, of course, actually, right? Because when you move across the period, effective nuclear charge becomes more important, which pulls the electron cloud strongly towards the nucleus, which decreases the electron cloud, and hence the size also decreases. Okay, so however, their size is bigger than the p block elements, but their size, whether the atomic size or the ionic size, it is smaller than the alkali metals. You should remember this particular point. Okay, and then there comes the beryllium. Beryllium differs much more than the rest of the group members than lithium does from the members of the group 1. As you know, the lithium has the significantly different properties and the anomalous behavior, and this behavior is quite different from the remaining members of the groups. Same is true for the beryllium also. This beryllium is having the anomalous behavior due to its very smallest size, actually. Okay, this size is very small for the beryllium, so it actually differs in the properties significantly from the rest of the members of the groups. Okay, and this difference in the properties is much more pronounced when you move from beryllium to magnesium than it is for your lithium to sodium. This is something very important. The main reason basically is that the beryllium atom or the beryllium ion Be2 positive, they are very small, actually. Okay, so when they are very relatively small when compared to the magnesium, in fact it is beryllium 2 positive, and if you go for the data wise, right, so I can write here, say for example, this is your Be2 positive, okay, and this is your Mg2 positive, right? So basically this magnesium is 4 times greater in size than the beryllium. Okay, that means it is extremely small. Okay, while this difference is see here 4 times, this magnesium is 4 times greater in size than the beryllium, but this much of difference in size is not there in case of the lithium and the sodium. That's why your beryllium significantly differs from the rest of the members of the groups. Okay, and like you can see, the your lithium shows the diagonal relationship with the magnesium. Okay, and then your beryllium, actually, if you move, the beryllium shows the diagonal relationship with the aluminium. We'll discuss the diagonal relationship if the time permits. Okay, these things are very important. Okay, now then comes to the see, and whatever the things I have explained, they are equally true for the atomic radii also. Okay, and then we can move further and go through the physical state, right? How actually they look like. Physical state is rather important. Okay, so basically they are also soft but harder than the alkali metals. As you can remember, or you can recall, in case of the alkali metals, I have shown you the video also. They can be cutted with the help of the sharp knife of the blade. Similarly, these metals are also soft, but they are comparatively harder when compared to the your first group member. So what is the reason behind this? See, reason is the metallic bonding. Okay, and if I go back again and again, I need this particular slide. You can see here 2 electrons are present in the outermost shell of every element present in the group 2 metals, that is in the alkaline earth metals. So these 2 electrons are involved in the metallic bonding, while in case of the alkali metals only 1 electron is there in case of the s orbital. So in case of the alkali metals, your metallic bonding is weak because only 1 electron was there, while in case of the alkaline earth metals 2 electrons are there in the s orbital, so their metallic bonding is comparatively harder than the alkali metals. That's comparatively stronger than the alkali metals. That's why they are hard when compared to the alkali metals, but still they are soft with the remaining metals. Okay, and this hardness decreases down the group, right, because the size increases. Okay, and when the hardness, see that since they are harder than the group 1 elements, so they are less ductile and less malleable than the group 1 elements. Ductility, ductility is the ability of the particular metal to draw the wire of that particular metal. Malleable, that means you can you can hammer that particular metal to convert it into the sheets. That is the malleable character. So the ductility as well as the malleability is little bit of the lower side, as they are little bit harder when compared to the group 1 metals, and this hardness decreases as we go down the group. So this is something very important. Okay, and after that, see what is there in the next slide. Okay, see ionic radii again. See, I have explained you. See here the difference is what you see, this lithium, it is the lithium atom, it is somewhere around 152 picometer, while lithium ion is 176 picometer. It is quite smaller, and you know the fact your cations are always smaller than their parent atoms, because in the formation of the cation you have removed the electrons. So the effective nuclear charge increases, which pulls the remaining electrons more strongly, which decreases the size actually. Okay, now if you go for the beryllium, so for beryllium it is 112 picometer, and when you form the beryllium ion, it is 31 picometer. So if you take the difference actually between the two, okay, so I can write here 152 and then the 76. So 6 is here and 76 is there. Okay, and if you write 112 here, so you can write 31 here. So 1 and then you can see here 81. So this difference is quite large actually. That's why beryllium ion actually is important. Okay, and you know the ionic radii also increases when you go down the group. Okay, so beryllium is smallest in size in the group. That's why it is having the anomalous behavior. Now moving to the next slide, and this is the comparison you can see here. See atomic radii of the lithium to, see if you check this atomic radii between lithium to sodium ion. See, this is again a very important data which you should know. 0.186 nanometer. Okay, and for lithium is 0.152 nanometer. So difference is what? 4 and 3. Okay, that means 0.034 nanometer is the difference. You can easily convert this nanometer into the picometer. However, I am not going to convert this. However, it would be rather important, rather good, or rather well if I put this value also in the nanometer, in the picometer, as I have quoted earlier. Okay, now if you check this here, beryllium and magnesium difference. So this is 0.160 for beryllium nanometer hai. Okay, and then this is 0.112. So this will give you 8 and this will give you 40. So 0.048. So this actually difference between the size of the beryllium ion and the magnesium ion, which actually gives the distinct behavior of the beryllium to the magnesium when compared to the lithium to the sodium. Okay, this already I have explained to you. And then what I have written here, let me check why group 2 elements are less reactive than the group 1 elements. Okay, this is due to the smaller in size. Okay, so as we move across the period, the reactivity actually decreases, which you should know, and their size actually, if you can see the group 2 elements actually, right? So group 2 element, they are having, see, lithium is 3, beryllium is 4. So here beryllium is smaller, and your sodium is 0.186 nanometer and your magnesium is 0.160 meter. So their size is smaller. Okay, and so when their size is smaller, so this difference in the atomic radii, you can see their atomic radii is smaller. That means their effective nuclear charge is very high. These elements are rather reluctant to remove their electron to participate in the reaction. That's why their reactivity is lower than the group 1 elements. This is again depends on the size and the effective nuclear charge, which is the very basic concept. Okay, so my next slide is the ionization potential or the ionization energy. For example, if I write the electronic configuration of the sodium, right? So this is Na and this is 11, and if you write the electronic configuration, it is nothing but 1s2, 2s2, 2p6 and 3s1. Okay, so if I supply some energy actually to it, right, so I can write ionization energy. Okay, ionization energy, so it will form Na positive. That means removal of the one electron, so it will attain the configuration of the neon, which is 10, which that means the 10 electrons are here. And then if you compare this with the magnesium, right, I can write the magnesium here. So magnesium is your 1s2, this is 2s2, and this is 2p6, and then your 3s2. Okay, 612. Okay, now see, if I supply one electron to this, okay, and then it will form the Mg positive. Okay, and we are having total 11 electrons. So why I have written these two configuration? It is something very, very important. So if you see here, first ionization potential of the alkali metals, are quite lower. Why quite lower? See, because they are having only one electron. If I remove one electron from here, actually it will easily attain the configuration of the nearest noble gas, which is the most stable condition for it. That's why very little amount of energy required to remove the electron from here. Okay, while for the group 2 metal, and you know, when you move across the period, so group 2 metals will have the lower size. So please remember, group 2 metals actually will having the lower size, or smaller size rather, lower or the smaller size. Since the size of the alkaline earth metals is small, okay, that means their effective nuclear charge is quite high, and due to this high effective nuclear charge, this magnesium is quite reluctant to remove the electron from here. So it will require higher amount of the energy to form the Mg positive ion. It is quite important. That's why if you compare the first ionization potential, then first ionization potential of the alkaline earth metal would be higher when compared to the alkali metals. Now, if you supply, say, little more energy to it, plus I can write IE, or IE second rather, it was IE first actually. So you might have formed Na2 positive, and you know, because since it has this sodium ion has attained the electronic configuration of the nearest noble gas, so this second ionization potential is quite high. Okay, but in case of the magnesium, if you supply some more energy, IE I can write, so it should be the capital E, sorry, this is 1 electron 5. Okay, and IE is there, right? And if you supply more energy, which is the second ionization potential, okay, so it will again lose the electron to form the Mg2 positive, and it will have the now 10 electrons. So second ionization potential would be quite lower when compared to the alkali earth metal. So this is the thing which you should remember, which I have summarized here also. First ionization energy of the group 1 elements are lower than the first ionization energy of the group 2 elements, okay, right, due to the size. Second ionization potential of group 1 elements are quite higher when compared to the group 2 elements. The reason is that which I have explained here. So this is something very, very important which you all should know, especially beginners. Okay, so this lecture is not only for the advanced learners, for the advanced learners of the advanced chemistry, but it is these lectures are also for the beginners, like the students who are studying in the class 11th or the class 12th or in the BSc. These lectures are equally important for them, because it is my general tendency, whatever the topic actually I upload in my channel, I actually complete the lecture thoroughly, right from the basics which is required for the beginners and up to the most advanced point, right, like your for CSIR NET or GATE or the other examinations. I hope this is clear to you. Now next is what? Beryllium compounds are typically covalent, while magnesium, calcium compounds are ionic. Again, see guys, this is something very, very important. So since I have explained this one, so I don't need this place, so I am removing it. Okay, fine. So why this actually happens? I already told you this beryllium Be2 positive, and you have already seen this is very, very small. Okay, so its polarizing power is very, very high. Its polarizing power is very high, and whenever the polarizing power is very, very high, it can easily polarize the anion, and your compound will have the significant significant percentage of your covalent character. That's why due to this extremely small size, your beryllium compounds are covalent, right? While magnesium, you can see the size is quite good. For calcium and so on, the size is quite good, and that's why they are ionic in nature. And this ionic nature of the compounds increases when you go down the group. So here you can see, as you have seen earlier, your alkali metals are very good reducing agents. Okay, and these alkaline earth metals, that means the group 2 metals, they are also a very good reducing agent, but their reducing character is lower than your alkali metals, because alkali metals are more electropositive due to the bigger size, and the size of the alkaline earth metals is quite smaller when compared to the alkali metals. That's why due to the effective nuclear charge, they are little reluctant to release their electrons. So that's why they are not that reducing in nature. And for the beginners, it is very important. If you go for the modern definition of the oxidation and reduction, that means decrease in the oxidation number, that means decrease in the positive charge. And how we can decrease the positive charge on the particular metal? By supplying the electron. So these two groups in the periodic table 1 and 2, they all can actually give the electron to the particular species, so they can act as the reducing agents. But please remember, alkaline earth metals are less reducing than the alkali metals. Please remember. Okay, so here you can see this is the reducing order, which is increases in that manner, because you see it is smaller in size. Okay, so when it is smaller in size, its reducing character is lower, and as we go down the group, the size increases. That means the removal of the electron becomes very easy. That means the metallic character increases, so the reducing nature also increases. Okay, but group 2 metals are weak reducing agents compared to the alkali metals. Okay, and the reducing character of any metal is best measured in terms of the electrode potential. Okay, so here see what actually you can understand from here. However, this thing I think I have also explained in my very short list of electrochemistry. I couldn't complete that electrochemistry lecture series, but I have explained this thing there also. Well, you should remember this particular point, right? And say, I am writing here, higher the value of reduction potential, higher would be the tendency of metal to get reduced. And when it is getting reduced, that means it is acting as a oxidizing agent. Please remember this point. In any redox reaction, the species which is undergoing reduction will act as an oxidizing agent, and the species which undergoes the oxidation will act as a reducing agent, right? And for alkali metals and alkaline earth metals, please remember, for both of them, the value of the reduction potential is quite low. Reduction potential value is quite low. Since the reduction potential of these two are quite low, that means they will not have a general tendency to undergo reduction, rather they will undergo the oxidation, and the species which is undergoing the oxidation will act as a reducing agents. Okay, but the value of the reduction potential of group 2 elements, you can see, is higher when compared to the group 1 elements. Since the value of the reduction potential is higher for them, they will have the higher tendency to undergo the reduction, and that's why they will act as a oxidizing agent. This is just for the explanation. However, they are not oxidizing agents, but this is just the explanation when you are comparing to the reducing nature with that of the group 1 metal. Okay, this is something again an important feature which you should remember. So whether it is calcium, whether it is magnesium, right, they all are very good reducing agent. Now moving to the next thing, metallic character. Okay, metallic character means simply the removal of the electron. Okay, so alkali metals and alkaline earth metals, as you know, when you move across the period, the size decreases, and when the size decreases, see, I can write here, when you move across the period, size decreases, and when you go down the group, the size increases. Okay, now you are moving from lithium to beryllium. That means size actually decreases. When size decreases, that means effective nuclear charge increases, and when effective nuclear charge increases, then the removal of the electron become little difficult, and when the removal of the electron become little difficult, that means it will form positive ion but with difficulty. That means lower metallic character. That's why alkaline earth metal are less metallic. However, they are they are again like alkali metal, they are silvery white, or sometimes not silvery but the white actually. Okay, so most metallic due to the alkali metals are more electropositive in nature. Please remember this particular point. Okay, and same is true for the electropositive characters. Metals have a tendency to lose electrons. This I have already explained to you, and this is the periodic variation, and you can correlate this with the ionization potential. Higher the ionization potential, lower the metallic character, which I have already explained to you. Okay, I don't think whether I should go again and again for the same kind of the explanation. Now moving to the next slide, what it says, melting and boiling point. Rather, see again, you can see here melting and boiling point. These alkaline earth metals are they are having the 2 electrons. Please remember, they are having the 2 electrons. When they are having the 2 electrons, that means their metallic bonding is strong. When their metallic bonding is strong, so they should have the higher melting point. Of course, a higher boiling point also when compared to the group 1 metal. It is something very, very important. So here you can see for alkali metals, if you go down the group, melting point decreases, and this is true for the alkaline earth metal also. Okay, so group 2 elements have the higher melting and boiling point than the group 1 elements. The reason is what? Because 2 electrons are present here, so metallic bonding is a little bit stronger here, and when metallic bonding is little bit stronger, it simply indicates that it should have higher melting at the boiling point. However, pattern is very, very irregular. These metals cannot actually follow the regular pattern, okay, of your melting at the boiling point, right? So why this irregular pattern is there? As I have see in case of the lithium, in case of the alkali metals, this is quite fine actually. See, lithium is the you can see this is having the melting point, and then your sodium, then potassium, rubidium, and cesium. Okay, so this is according to the size. This is quite fine. But in case of here, you can see melting point of beryllium. After beryllium, there comes the calcium. There is no place for the magnesium. Okay, and then strontium, barium, and the magnesium goes last. And similarly, if you see for the boiling point, then beryllium. After beryllium, then you are having the barium, and then calcium, and then this one. So pattern is not regular in that case. Okay, see these metals actually, right? They have the different crystal structures. When they have the different crystal structures, that means crystal structure, when the crystal structures are different, definitely their lattice energy would be also different, right? And due to this, irregular pattern is observed. Fine. So now moving to the next slide, density. Your another important aspect is the density. So for density, you can see here alkaline earth metals, they have the low densities. For density, you know, simply density equals to mass over volume. There is no problem in that. Density equals to mass over volume. That means when this increases, this decreases. So when you move across the period, your size decreases. And when the size decreases, definitely density increases. Okay, that means your alkaline earth metal should have higher density than the alkali metals, and it is true also. Alkaline earth metals are denser than the alkali metals due to this particular concept. Okay, down the group, the atomic masses increases. You know, when you move down the group, whether it is whether you are observing for the alkali metals or the alkaline earth metals, it will not make any difference. Okay, so down the group, atomic mass increases, which more than compensates the bigger atomic size. Therefore, that's why the density is less than the density of the magnesium. Why actually this is happening? Okay, fine. There is nothing. See, next thing is quite simple. This I have already explained you in my first lecture also. See, when you move down the group, both things increases. Your atomic mass increases, as well as your atomic size also increases. But which one is the dominating factor? right? That dominating factor will decide the density basically. So what I have written here, down the group atomic mass increases, which more than the compensates the bigger atomic size. That means it will compensate the atomic size. That means the atomic size also increases, but that increase is not that much when compared to the atomic number. So atomic number increases, that means mass increases, so density also increases, right? That's why down the group density increases. This I have explained to you. Calcium is less denser than the magnesium because of the presence of the penultimate d orbital. This is rather simple. I have this is written here actually. See, density of the calcium is lower than the density of the magnesium. It is written here. Okay, there is no problem in that. So what it says, you know, the atomic number for this magnesium is 20. It is for 12. If you write the electronic configuration, somewhere after that it will have the 3d orbitals vacant. Okay, vacant 3d orbitals. That means volume increases. Volume increases. When volume increases, definitely density decreases. That's why magnesium is having the lower density, calcium is having the lower density than the magnesium. This was quite simple. Now moving to the next thing, which is the flame coloration. Flame coloration I have also explained in case of your alkali metals, but here you can see, if you see here, I have from where I have started. I have started from the calcium, and then strontium, and then barium, and the radium. So I didn't include the magnesium here, and I didn't include the beryllium here. That means beryllium and magnesium, they will not give the characteristic flame to the color. Why? Because their ionization potential is quite high, and very high energy is required to remove the electron from them. So that's why your beryllium and magnesium will not impart any color to the Bunsen burner or the Bunsen flame actually, right? While your calcium is brick red, okay, and strontium is your crimson red, and your barium is apple green, and radium is the crimson. So these colors are there. So these properties generally shows only in the S block elements. D block elements do not impart any color to the Bunsen flame. This is again important thing here. Okay, and their color are rather pale actually, because their potential, their ionization potential is quite high. So high energy is required. So they are not give the very bright color like you have observed in case of the alkali metals, but in that case the colors are little pale when compared to the alkali metals. Okay, now moving to the next important property. Okay, so now let's move on to the chemical properties of your group 2 metals. Let's see what is the first chemical property of this. First is the reaction with the oxygen, right? So basically what I have written here, oxygen with air. You know, the air also contains the nitrogen, and nitrogen is quite unreactive. So we later on we will also see the reaction with the nitrogen. First of all, you can see here all the metals of group 2 elements will actually group 2, right? All the metals of the group 2, they will combine with the oxygen to form the metal oxide. Okay, and you can see here just beryllium combined with this one, and it forms the beryllium oxide. Similarly, magnesium combines with this one, it forms magnesium oxide, right? All these reactions are here, and you can see here beryllium, magnesium, and calcium. If you go through the first three actually, beryllium, magnesium, and calcium, they when heated with the oxygen, they form the monoxides. Please remember this point: beryllium, magnesium, and calcium, they only form the monoxides because their size are comparable with the oxide ion only. So they can accommodate only the oxide ion, or they can only cater the oxide ion, so they'll form only the monoxide. Okay, right, like I have written over there. While your strontium and barium and radon, however, we can exclude the radon because it is radioactive, so we rather use this compound. Okay, but it is true that the strontium, barium, and the radium, they also form the peroxide. Why? Because their size is little bit bigger than when compared to the earlier three members, so they can cater the bigger oxide ions also. So that's why they also form the peroxide. It should be it should be noted, and it is very important. and the reaction is MO2 type. You know, this is the formation of the peroxide, and these are the formation of the monoxide. Okay, so this is, you can see the M2O2 whatever I have written here. Okay, so this reaction is very important. So the important thing is that when you expose these metals with the air actually, so they readily form these oxides, and due to the formation of these oxides actually they achieve the crystalline nature, or crystalline, they become the crystalline solid, and these oxides are basic in nature, but not your beryllium oxide. As at the start of the lecture I already told you that the beryllium oxide nature is not alkaline, that's why it is excluded from the list. Actually it is not a true alkaline earth metals, right? This I have already explained to you. And see, the basic strength of these oxides basically increases when we go down the group. This I have already explained to you. Now you can see one more important aspect here. If you have beryllium oxide, right, say, so the important thing about these oxide you should know, this is your beryllium oxide, right? This beryllium oxide is very hard in nature, okay, and this is having the coordination number of 4:4. That means one beryllium is surrounded with the 4 oxygen, and 1 oxygen is in turn surrounded with the 4 beryllium. So 4:4 is the coordination number for this one. While for rest of the oxides, if you take the magnesium oxide, like if you take the calcium oxide, their coordination number is 6:6, obviously due to the bigger size, okay, due to the bigger size of these metals. So 6:6 coordination number is there in that case. And these oxides, whether it is your beryllium oxide or magnesium or calcium oxides, they are quite stable, okay. So why? Because they are having very high lattice energy. Due to their very high lattice energy, these oxides are very stable, right? And if you take one more important data, like you are having your, say, beryllium oxide, okay, sorry, beryllium oxide and your magnesium oxide, right? These two are water insoluble. They are insoluble in water, okay. And while rest of other oxides are soluble in the water, and the basic strength increases down the group, as I already told you for them. And see what actually happens in case of this magnesium and the calcium oxides. If you remember, or if you have learned, or if you have studied your metallurgy part, then you know the calcium oxide and the magnesium oxide, these two, right? If I write here calcium oxide and magnesium oxide, these two are used in the linings of the furnaces when you do the metallurgy. Why? Because their melting point is quite high. So basic lining, so basic nature lining which are there in the furnaces, actually in that case your calcium oxide and the magnesium oxides are used because they are having the very high melting point, okay. And then you can see here, we can move further. Here you can see the very important reaction which actually I have missed actually to explain. So this magnesium, when it is reacting with the air, and I already told you just a few moments back, this air contains the oxygen as well as the nitrogen. So when the magnesium combined with the oxygen, it forms the magnesium oxide, as well as when it combines with the nitrogen, it forms the magnesium nitride of the type Mg3N2. This actually reaction is a exothermic reaction, and it produces a very important, very shiny, beautiful dazzling flame, okay. And this dazzling flame is used in the flash photography. You can see the picture here. This is the dazzling flame which is produced by this particular reaction, because it is exothermic, actually it catches fire, it gives you the flash like that, okay. So this method is used in the flash photography. This is something very important. So I have written here, you can see, okay, this I have completed. Then next is the reactivity, okay. Massive form or the big crystals of the beryllium only reacts with the above 600 degrees centigrade. That means towards oxygen your beryllium is unreactive. So that means if you want to produce beryllium and you want to burn that beryllium in the oxygen, so that would be a very hard reaction, because beryllium only reacts with the oxygen after or the above 600 degrees centigrade. See, if you have the big crystals of the massive or the massive forms of the beryllium, but if you finely divided this crystal into the fine powder, when we have the grains are having the much larger surface area. So due to this larger surface area, reaction rate goes higher. Okay, so when you convert this massive form into the powder, only then you can burn your beryllium in presence of the oxygen to get the beryllium oxide. Otherwise it is not possible. And next, as you can see here, thermite reaction basically. Okay, so what are the thermite reactions? Thermite reactions are the reactions in which the metal oxide is reduced to metal by using the aluminium as reducing agents. So you can see metal oxide is reduced to the metal by using aluminium as reducing agent. This is the thermite reaction, very famous thermite reaction. Okay, so this magnesium oxide is also used in the thermite reaction also. This is something very important. Why? Because when magnesium burns, it forms the magnesium oxide, and that this magnesium oxide can be reduced to the magnesium by using the aluminium. This is used in the thermite reaction. This is another very important aspect which you all should know. Now moving to the next property. Okay, reaction with the nitrogen. So one very important thing about the reaction with nitrogen I have already explained here. Okay, now moving to the next one. Here you can see what it is saying. Okay, if you have followed my last lecture, which I have uploaded day before yesterday, okay, there I have explained that lithium forms. See, among your first group elements, like your alkali elements, only lithium forms the Li3N, that means lithium nitride directly. Okay, but in case of the group 2, metals, all metals will form the nitrides. Why? Because their size is smaller than the group 1 metals, and the nitride actually is the N3 negative is the quite small one, so it can readily formed, this nitride are readily formed by the group 2 metals when compared to the group 1 metals. In the group 1 only lithium can form such nitrides. As we go down the group, the size of the metal or the ion increases, therefore the nitride formation tendency decreases. Please remember, when the size of the metal, ion or the metal increases, then the nitride formation tendency decreases. For the alkali earth metals, while there is no question of this decreasing reactivity or decreasing order in case of the alkali metals, because only lithium can form the nitrides. Okay, this is something very, very important. And why actually this happens? This is another, there is another very important aspect here. You can see lattice energy is high for these magnesium nitrides. So whatever the nitrides you will form, for them lattice energy quite high. Why lattice energy is quite high? The high charge is present on the metal, like these all metals are 2 positive, and your nitrogen is 3 negative, this high charge. Due to the presence of this high charge, this crystal is very, very strong, the lattice energy is quite high. Okay, and the nitrogen is very, very stable, and we need very high energy to form the N3 negative. So from where we can get this high amount of the energy? Actually, this high amount of the energy comes from the lattice energy when your nitrides are formed. So whenever the nitrides are formed, the energy is released, and that energy is utilized by the nitrogen to convert nitrogen into the N3 negative. Okay, so this concept, this basic concept you should also know. Okay, this is something, another very, very important aspect. And here I have written the ease of formation of nitride decreases from beryllium to barium. Okay, fine. Earlier in the slide, I have already told you, these are not my slides, these are the downloaded slides, but there was an error in that case, right? So it is not increases, it is decreases, as I have given you the explanation for this. I hope this is fine. Now moving to the next one. So when these nitrides are dissolved into the water, they forms the hydroxides, especially this is the magnesium hydroxide, and they liberate the ammonia. So whether you do the reaction with this one or with the calcium nitride, it will always eliminate or evolve, not eliminate, evolve ammonia, and metals get dissolved into the water to form the hydroxides, basic hydroxides. Okay, now moving to the next one, reaction with the water, reaction with water or the moisture. Another very important aspect, metal. You take the two equivalents of the metal, they react with the two equivalents of the water, and they form the magnesium hydroxide of MOH whole twice type with the evolution of the hydrogen. That means from the water they can remove the hydrogen. So if you write the reaction with any of the like say you are having say magnesium, okay, and you are dissolving your magnesium into the water, so it will form magnesium hydroxide and it will liberate hydrogen gas. So 2 and 2, 4 hydrogen atoms are required, so you should take 2 of this one, and when you take, then the oxygen becomes 2, okay, and Mg, okay, fine, this reaction is quite fine. So this hydrogen evolution occurs actually, and the reactivity with the water of these metals increases when we move down the group. Okay, this is the same region or the same explanation. See, as you know, the reactivity increases down the group, so it is true in that case also. Fine. And you can see the beryllium does not react with the boiling water. This is something very, very important. Beryllium, as I already told you, beryllium is very, very special due to its very smallest size. So beryllium actually does not react with the steam. It will not react whether you take the cold water, you take the boiling water, or you take the fuming steams, right? So beryllium is unreactive at all. While magnesium will react only with the boiling water. That means if you pass the steam over on the magnesium, only then you will get the magnesium hydroxide. Okay, so this should be steam, right? So I should have write here steam. While calcium, strontium, and barium, they react vigorously with the cold water. If you take the cold water, they react with vigorously with them. Okay, so this you have to remember. Now you can see the solubility. You can see for the solubility, please remember, down the group the solubility of these metals increases. Okay, when you dissolve into the moisture, down the group in the water, the solubility increases for these metals. And when the solubility increases, in the same manner your basic nature also increases, right? And why this happens, you can see here. As we go down the group, we know the size of the metal increases, and when the size of the metal increases, lattice energy decreases, rapidly decreases. This I have already explained to you in my last lecture also. But if you haven't seen that particular lecture and you are following this lecture for the first time, then you should remember, down the group lattice energy decreases, okay, and your hydration energy also decreases. So all things, see, when the size increases, hydration energy decreases, lattice energy decreases. Now which one would be the deciding factor, right? Will decide the solubility. Okay, so in that case you can see the hydration enthalpy decreases, but it decreases rather slowly. But this decrease in the lattice energy is quite sharp, right, and quite high. So it is a dominant factor, right? It is a dominant factor, and when it is a dominant factor, it will increase the solubility. Okay, and when your hydration energy is the domination factor, then it will decrease the solubility. So in that case, you can see here, when we move down the group, as we can see, the solubility increases, right? So why the solubility increases? Because your lattice energy much more rapidly than that of the hydration energy. And your beryllium hydroxide, I already told you, it is amphoteric in nature. That's why beryllium is not included in the true alkaline earth metals. Okay, and then there comes the magnesium hydroxide, which is your antacid. So that is MOM, milk of magnesia, right? So why the milk of magnesia? Magnesia is the trivial or the older name of the magnesium, and the hydroxide of this appears like actually milk. It is white in color, so that's why the name is given milk of magnesia, and it is antacid. So if a person is suffering from the slight constipation, right, not the chronic constipation but the sudden constipation, then for this your magnesium hydroxide is used. So what this magnesium hydroxide does, this magnesium hydroxide actually absorbs the moisture from the intestine and loosen the stool, and the bowel movement will occur now properly, and the person will have the relief after taking this magnesium hydroxide. The person will have relief from the constipation. This is another very important application, but remember, you can never use barium hydroxide, as your barium and beryllium are toxic in nature. So we can never use the barium hydroxide for this one. So this I have written here, barium hydroxide, which is toxic, most soluble, and as strong as alkali, as NaOH. So it is just like as strong as NaOH as alkali. Your metal reacts with the hydrogen. If you heat these two together, they will form the metal hydride. Okay, like magnesium form the magnesium hydride, and calcium form the calcium hydride. And the technical name of calcium hydride is the hydrolith. Please remember, you may have the objective type of the question in your competitive examination. What is hydrolith? Hydrolith is the calcium hydride, which you should remember. Okay, this is another very important thing. And beryllium hydride, BeH2, can however be prepared by reducing beryllium chloride with the lithium aluminum hydride. It's a very strong reducing agent. Why this happens actually? Because this beryllium, due to the smaller size, it is quite unreactive towards hydrogen also. So if you try to heat this beryllium with the hydrogen to get the beryllium hydride, then the reaction is not possible. So for the synthesis or for the preparation of beryllium hydride, you have to react with the beryllium chloride. First you convert beryllium into the beryllium chloride, and that beryllium chloride with the beryllium chloride is reduced with the help of the lithium aluminum hydride to get the beryllium hydride. Okay, so this is the reaction which I have written here. Okay, so this is something very, very important, and this reaction should be there in your notes also. Okay, so all the hydrides react with the water to evolve the hydrogen and thus behave as the strong reducing agents. As I already told you, whatever the hydrides are there, they react with the water with the evolution of the hydrogen. Since they are evolving the hydrogen, this hydrogen actually can add up to the certain reagent and reduce that particular substrate. Okay, so it is this magnesium hydroxide also reducing in nature. Okay, so here I have written beryllium hydride and the magnesium hydride. Beryllium does not react with the hydrogen, as I have already explained to you, and these two are covalent in nature. Please remember, these two are covalent in nature, and polymeric bridge structures are there for this one. And calcium hydride is technically known as the hydrolith, and all these are ionic in nature, while the first two are covalent in nature. And the stability of these hydrides decreases down the group as the size of the metal increases. Okay, now moving to the next slide. Before going into the next slide, I should have been given the structure of these, right, polymeric structures. So you can see how you can go for the polymeric structures, right? These polymeric structures are very, very important. So I may be given this structure in the upcoming slides, but right now you can understand it in that manner. You are having this beryllium. Okay, and again you are having this beryllium, and say you are having the polymeric chain of beryllium like that. Okay, so what you can do, you can place hydrogens over there. In the middle of the two beryllium atom, you can put your hydrogens. Okay, and then connect them to get the bridged structure. So this is hydrogen, this is hydrogen, this is hydrogen, and this is hydrogen. So it's a polymeric structure. And this polymeric structure is basically two-centered, is having the three-centered two-electron bond, 3C2E bond, right? And in case of the borane or the diborane, you have learned about this 3C2E bond, electron deficient compounds. So it forms a banana bond. If you go through the hybridization and the orbital picture, then you will be able to know what is the banana bond. If you don't know what is the banana bond, I'll discuss this in the upcoming lecture. So please remember, see, three center bonds are present in which your banana shaped molecular orbitals covers three atoms. Like what three atoms? Like you see your beryllium, hydrogen, beryllium. So this is actually the shape. This actually looks like the shape of the banana. So I can draw the shape of that banana just like that, right? This is your banana bond. Okay, and this contains only two electrons. So it's a three center two electron bond, where actually this hydrogen which is there, actually it is lie in the perpendicular plane to the plane of the molecule, right? If you see the 3D structure, and the stability of these hydrides decreases as we go down the group, which I have already explained to you. Okay, now moving to the next very important property, solution in liquid ammonia. Okay, fine. So solution is liquid ammonia is another very important aspect, and this I have already told you in my last lecture, where I have explained you the color actually. So in that case, what is written here, like alkali metals, the alkaline earth metal dissolved in the liquid ammonia to give the deep blue color, okay, solution, forming ammoniated ions. So these are the ammoniated ions and these are the ammoniated electrons. But the explanation is, see, in that case the explanation is not very proper here. So what you can do, you can learn that explanation from my last lecture, where I have explained what happens with the concentration. See, initially when the solution is dilute, that means less ammonia is there, the solution is actually not that deep in color, but you keep on adding ammonia to it and the solution becomes concentrated in terms of the ammonia, then the color actually deepens, and this is true here also. You should know this point. Okay, so what basically happens, these alkali metals can also dissolve in the liquid ammonia to form the colored solutions, right? And dilute solutions are bright blue, as I already told you, which is not written there on the particular slide. Okay, and when you keep on concentrating the solution, that means by adding the ammonia, then this color deepens and it converts into the deep blue color. Only then, not initially. Only then, not initially. So slide is not actually the perfect in that case. Okay, and okay, from these solutions, the ammoniates, right, this one can be recovered, but concentrated solutions are bronze colored due to the formation of the metal clusters. Okay, so where the metal clusters are formed, actually this is something very important. Say what are the reactions? So what you can do, you can understand the reaction sequence also. Say for example, I am having the alkali earth metal, for example I am having the say calcium I am having. Okay, I am writing the reaction in that manner. You can use the instead of calcium, you can use the magnesium or the strontium also. So what will happen? It will form the calcium 2 positive ion and will liberate 2 moles of the electrons, or 2 equivalents of the moles of the electrons, not equivalent, sorry, 2 of ammonia, which is present as the solvent. It will grab these electrons, okay, and then hydrogen will be evolved from here, gas, and you will form the amide ion, 2 of NH2 negative, right? And after that, what can happen, the metal ion which you have formed in the first reaction, like calcium, they can react with these amides, okay, to form the metal amides. This is NH2 whole twice, right? This is the specific reaction about the calcium, but you can generalize it by taking M instead of the calcium, or you can replace this calcium with the magnesium or the strontium or the barium, whatever. Okay, so what actually happens, actually these reactions happens in the solution, and when the solution is evaporated, okay, when this solution is evaporated, so what I can do, I can write like that, evaporation. So what when evaporation occurs, actually, so this convert into the hexa NH3 whole 6, right? This compound is formed actually, right? And this compound slowly decomposes into metal amides like M, NH2 whole twice, or since I have used calcium here, so what I can do, I can replace this with the calcium. Here ammonia will liberate from here, 4NH3, and hydrogen gas. The reaction goes like that, and concentrated solution of the metal actually are bronze in color, which is written here like that. So this is the ion, you should remember. Okay, so I have written in that case just like that. So where I made a mistake, 2 positive, sorry, I should have written like that. So this reaction sequence is already also important for you. Okay, now moving to the next slide, and of course before concluding this particular slide, you should know these are the good conductors of the electricity, because they are having the electrons, ammoniated electrons, okay, and the charge ions. right? And see, however, this property is much less pronounced in that in case of the alkaline earth metals, but it is more pronounced in case of the alkali metals. Halides, right. This we have to cover in pretty much detail, because these halides are rather important, and generally students have the question from this section in the examination, whether it is the academic examination or the competitive examinations. You'll always have the question from this particular section. And please remember one more thing. If see, these actually group properties are very tedious and very fast, very vast. So there may be every chance that I have missed some questions, but whatever I will miss, I will definitely cover in the question answer sessions, right? So you continue to follow my lecture actually. Yes? Please continue to follow my lectures so that you can have the complete knowledge about the groups also. And these groups are very important. So in that case, you can see what is written here. Except for the beryllium halides, okay, all other halides of the alkaline earth metals are ionic in nature. I have written here. Beryllium is more covalent in nature, and similarly magnesium is also having the significant covalent character, while your calcium, strontium and halides, they are more ionic in nature. So you know the Fazan's rule, polarization, the polarizability, and you know no bond is perfectly ionic, that is 100% ionic, and no bond is 100% covalent, and you have to apply the Fazan's rule where you can find the percentage ionic character in the covalent compound. So based on this Fazan's rule, you can say that beryllium and magnesium halides, they are more covalent in nature. That means they are having the more covalent character than the ionic character, and remaining calcium, strontium and the barium halides, they are ionic in nature. If you don't have any idea about the Fazan's rules, I am giving you the link in the description box, okay, and you can check the Fazan's rules. I missed the actually I forgot to put the link in my earlier alkali metal lectures, so I will also put the links over there, which I have promised to give you in the description box in my last lecture. Okay, when it comes to the solubility in the water, then these MX2 are the water soluble, okay, and the solubility decreases as we go down the group, okay, and you know the your barium halides are less soluble, okay, and why this happens actually, because hydration energy also decreases when we move down the group, okay. But you know, when we are moving down the group, so ionic nature or the ionic character increases, and when the ionic character increases, it simply means that this will have the higher melting point, and conductivity also increases. So conductivity down the group increases, melting point down the group increases for these halides, okay. And they all are hygroscopic in nature. Hygroscopic means degree of deliquescent nature. That means the ability to absorb moisture from the atmosphere. And you know this calcium chloride, which we use in the desiccator, it is a very famous dehydrating agent. So if you are in BSc actually, right, so you must be aware about the desiccator. Desiccator is a glassware which is used to drying the chemical compounds, and if you want to absorb moisture from the chemical compounds, then you use this calcium chloride as the dehydrating agent. It's a very famous one, okay. So your metal fluorides, right, so all your metal fluorides, so I have written Me here, it should be M actually, right, not E. Metal fluorides are exceptions, they are water insoluble, right, because these metal fluorides are much more covalent in nature, because fluoride is smaller one, right, and your metals are already there, so they are having the significant covalent character, so they are water insoluble. But among this, your beryllium fluoride is the exception, it is water soluble. Beryllium fluoride is the exception, which is water soluble. This is something very important. So you should remember the certain things actually, right? See this beryllium fluoride, as I already told you, this beryllium fluoride. So it is very water soluble. If you put this beryllium fluoride in the water, it is quite readily soluble. Why quite readily soluble? Because solvation energy is very high. So why this happens? So basically what happens actually when you take the beryllium fluoride, okay, BeF2, and if you try to dissolve this into the water, so what it results actually, it results BeH2O4 2 positive, okay, and it is having very high solvation energy of beryllium, okay. So this happens actually, then that means very high solvation energy is there in that case, and due to this this is readily soluble in the water, while in case of metal fluorides like magnesium fluoride, calcium fluoride, this is not true, okay. So this is soluble while rest of the members are insoluble, like say if you are having magnesium fluoride, right, and if you are having calcium fluoride, okay, if you are having strontium fluoride, if you are having barium fluoride, F2, BaF2, they are insoluble in water, and this is readily soluble due to the formation of this particular ion. This is something very, very important, okay. And now you can see here fluorides of the other metals like these, they all are ionic in nature. Please remember, they are ionic in nature, they are having the very high melting points, okay, but they are water insoluble. So it is a little bit of in the contradictory side. Generally ionic compounds are soluble in the water, right, but these metal fluorides, though they are ionic in nature, but they are insoluble in water due to the very low solvation energy. So when solvation energy is very, very low, that means your compound will not dissolve into the water, and in that case your solvation energy is very, very high. In case of the beryllium fluoride, that's why it is water soluble, so high solvation energy. In that case you can see here beryllium chloride is there. So if I go back, right, you can see these are the beryllium hydrides, these bridge structures, okay, and here also you are having the bridge structure of the beryllium chloride. Both actually are looking same, but they are not same actually, they are different. So this is this need to be understood. So when you are beryllium chloride in the solid state, please remember, when beryllium chloride in the solid state, it forms a polymeric structure, which I have shown you here, just like your beryllium hydrides, okay. And after that you can see if beryllium chloride in the vapor state, right, then in the vapor state it can form the dimer or it can form the monomer. So I have shown you the monomer here, and similarly you can also form the dimer here. But this compound is little different from the other types of the compounds. Let's check whether I have written in the, so you can see here what is my first question. Why beryllium fluoride is water soluble? Okay, this I have discussed, guys, okay. Due to the very high solvation energy, beryllium fluoride, though having the covalent character, but it is water soluble, okay. So actually I forgot that I put this question here, because I prepared these slides way long back actually. I forgot what I have put it in that slide and what not. That's why this problem is there. So it is soluble, see, though covalent, so I am writing though covalent, highly covalent, okay. It will have the certain degrees of the ionic character also, but due to high solvation energy, it is water soluble. So the next question is how BeCl2n differs from the BeH2n. See, both actually will have the three-centered bond. Please remember, both having the three-centered bond, and they are looking quite similar, but they are different, right? So if you remember, in case of I was having three-centered 2-electron bond. Why? Because hydrogen is not having any electron. It is electron deficient. It is not having electron. But in case of the halogen, you are having what? Lone pairs. So when you are having the lone pairs, that means the lone pairs can be easily donated to the beryllium. So if I draw the dimeric structure, like see beryllium here, and your another beryllium is here, and you are having the, say, one chlorine here and your another chlorine here. So what it can do? This chlorine can donate electron to this one, okay, and this chlorine can donate electron to this one. So actually the bond pair is coming from the halogen itself, and this is the normal bond, this is the normal bond, right, and then you have Cl and Cl. So in that case actually no banana bond, no banana bond. While in case of the hydride, you are having the banana bond. So this needs to be understood. So basically, what happens actually when this bridge is forms, in which a halogen atom bonded to the one of the beryllium atom uses a lone pair of the electron to form the coordinate bond, while this is not possible in case of the hydrogen. Right? I hope this is clear now. Now next is what? Anhydrous beryllium chloride cannot be prepared in aqueous solution. Why? Okay, that means, see, if you want to prepare, say, magnesium chloride, okay, or if you want to prepare calcium chloride, so you can easily form in the aqueous chemistry, right? In the aqueous solution, you can easily form them in the aqueous solution, right? And but if you want to synthesize them, or if you want to form them, if you form a beryllium chloride in the water, then it is not possible. And why it is not possible? I already told you. It actually takes up water and to form a complex ion. Okay, that's why it is not possible. So well, in aqueous solution, what actually happens? Your beryllium forms these ions. This I have already told you a few moments back actually. So you know it is tetrahydrated beryllium complex. Okay. So actually this compound results instead of your beryllium chloride, if you take the halogen acids along with the water, right? So this compound formed instead of your beryllium halide. And if you want to say suppose it is present in the form of this halide, right? Say for example this present like that, Cl2 is there. So when I am putting the Cl2 here, so what I can do, I can remove 2 of the charge from here, and say from this compound, if I want to decompose it, right? Say for example, if I heat this particular complex of the beryllium, so it will result in the beryllium hydroxide. Okay, and 2 of the HCl will remove from here, 2 of HCl along with the water. So you are not getting your beryllium chloride. Okay, so it is not possible in the aqueous solution, while this is possible in case of the other alkali metals, but in case of the beryllium chloride or beryllium halide, it is not possible. So basically your anhydrous halides, they are best prepared by the some other different reaction. You can take the, say if you want to synthesize it, so let me give you the thing. So if you want to synthesize this beryllium chloride, so you can better take your beryllium oxide and you combine this beryllium oxide with the carbon in the atmosphere of the chlorine. Okay, of course your high temperature is required in that case, around 700 degrees centigrade. Okay, only then it will convert into the beryllium chloride and your carbon monoxide, right? This happens like that. Or sometimes you can take your organic solvents also. So for example, you are having the beryllium oxide and you are taking your carbon tetrachloride. Okay, so in that case also, however, the higher temperature, again somewhere around 800 degrees centigrade is required. So it will form the 2 of the beryllium chloride, 2BeCl2. Okay, and carbon dioxide would remove from here. Since 2 to the 4, 2. So 2 of beryllium oxide is required here. And structures actually I have already explained to you. Your beryllium chloride in the vapor stage, it will exist as a monomer or the dimer, that is BeCl2 or BeCl2 whole twice, while in the solid state it is polymerized. But the structure of the polymerized form of the beryllium hydride and the beryllium halide is different, as I have already explained to you. Okay, now moving to the next slide. Industrial applications of calcium fluoride. Calcium fluoride is white. You should know the color of this particular compound, right? It is a white solid and insoluble high melting solid. White, high melting point solid, and it is water insoluble. Okay, please remember it is water insoluble also. And it is very important. So why it is important? Say you are having the calcium fluoride, CaF2, and if you dissolve this calcium fluoride in the acid, because it is not soluble in the water alone, so it will give you the hydrogen fluoride, HF. And you know the HF is used in the scratching of the glass. CaSO4 it will result, and you know this is used in the scratching of glass. So this is important application of HF, which is coming from the calcium fluoride. Okay, and this hydrogen fluoride which is formed here, if it is combined with the potassium fluoride, so it will form your potassium hydrogen fluoride. And if you do the electrolysis of this one, so you'll get the fluorine. Okay, and you know the fluorine is having large number of the industrial applications. So basically this calcium chloride, one more application of this calcium fluoride is what? In the spectrophotometer, cell windows for spectrophotometer. Okay, and it is also used in the making of the prism. Okay guys, so next important compounds of alkaline earth metals are the salts of the oxo acids. That mean the salts which contains the oxygen atoms, they are known as the salts of the oxo acids, and the main examples of these oxo acids are the carbonates. And these carbonates are very important when it comes to the water hardness. See, in a little while I will also discuss the hardness of the water. Okay, so what you can see here, alkaline earth metals, they also form the salts of the oxo acids, and carbonates of the alkaline earth metals are insoluble in water. So whatever you are having, say if you are having your calcium carbonate, okay, and it is water insoluble. In fact, in case of the water treatment, when you do the water chemistry and you are looking for the water hardness, this calcium carbonate is the most insoluble substances in that case. Okay, and it will not cause any kind of the hardness. Later I will discuss why. Okay, and similarly you may have your magnesium carbonate. Okay, and like that you may have your strontium carbonate. So various carbonates are there, and these all carbonates are insoluble in water. If you try to dissolve these carbonates in the water, then they remain insoluble one. However, if you pass the carbon dioxide through the saturated solutions of these carbonates, they can be made dissolve. Okay, why? Because they form the bicarbonates. In that case, you can focus on this particular reaction. Say my calcium carbonate is there, which is the most insoluble substance during the water hardness. Okay, and if you try to dissolve this into the water, it will remain undissolved or insoluble. But to this particular saturated solution, if you pass the carbon dioxide gas, then this carbon dioxide dissolve. Why? Because this calcium carbonate dissolves, because calcium bicarbonate is the product in that case. Similarly, you can do this reaction with your magnesium carbonate as well as your strontium carbonate. Okay, so this is how you can prepare. What you can do, you can take these carbonates, right, and you can prepare them, you can dissolve them by using this particular method. So this is something very important. Okay, so in this way carbonate dissolved in the water, which contains actually the carbon dioxide. And you should know a very important thing. So basically, if you have these carbonates, right, say you are having the say you are having magnesium carbonate. Okay, this is something very, very important. Okay, and you may have your, say, calcium bicarbonate, which you have just seen here in that case. Similarly, you may have the magnesium bicarbonate. Okay, so these bicarbonates generally present in the water sample, and they causes hardness in the water, and the hardness which is due to the soluble carbonates and the bicarbonates of your metals, especially calcium and magnesium, they cause the temporary hardness. Please remember. Okay, so I have made an extensive lecture series on the water chemistry and the water hardness. So I'll not discuss the details of the water hardness in that case. And if you want to know how the water chemistry goes, then you can type water treatment by tetrahedron chemistry classes in the YouTube search bar. You will get the results. Okay, so I have discussed all these things there, which you should remember. Okay, now the next very important thing is what you see what I have written here. The solubility of the carbonates in water decreases as the atomic number of the metal increases. So what is the meaning of that? Say, let me quickly remove all the things. Okay, say you are having, so you can see here, you are having your beryllium carbonate, and after your beryllium carbonate you are having your magnesium carbonate, and after magnesium carbonate you are having your calcium carbonate, and then you are having your strontium carbonate, and then lastly you are having your barium carbonate. So these are the carbonates, and as you go down the group the solubility decreases, right? So if you go down the group, then the solubility decreases. So why the solubility decreases? See, as the atomic number increases, earlier in this particular lecture I have already explained to you, when the hydration energy decreases, the solubility also decreases. Okay, so you should remember this particular point. So the insolubility, why this solubility decreases as we go down the group? Because decrease in the hydration enthalpy. And then after that you can see all the carbonate decompose on heating to give the carbon dioxide. Again this you should remember, whatever the carbonates are there, I can take the example of the calcium carbonate. Okay, if I heat this calcium carbonate, please remember it is something very, very important. If I heat this calcium carbonate, so it will decompose to calcium oxide with the liberation of the carbon dioxide gas. So this is a very, very important reaction. Why? Because this calcium oxide is also known as the lime. So if you want to prepare, or if you want to produce lime, then you can produce lime by the decomposition of the calcium carbonate. In the similar way you can decompose this magnesium carbonate, right, to produce your magnesium oxide, right, and so on. And the important thing is that, see, along with this your oxo acids like your carbonates, these alkaline earth metals also form the nitrates. Okay, and here what you can see, what I have written here, all the carbonate decomposes on heating according to this particular reaction. And here you see the important thing is that I have explained for the calcium, and I also told you that you can do the same thing for the magnesium carbonate and the strontium carbonate and barium carbonate as well. But beryllium carbonate is unstable and can be kept only in the atmosphere of the carbon dioxide. That means this kind of the decomposition actually would not be possible. Why? Because this beryllium carbonate is having tendency to absorb the moisture from the atmosphere. Okay, so it is actually quite unusual. So it gets hydrated. If you keep this in the absence of the carbon dioxide, it will take the moisture from the atmosphere. Okay, and it will get converted into this tetrahydrated ion. Okay, so I can put Be2 positive. This actually product or this complex ion you have seen already many times earlier in my lecture. Okay, so you will not find this Be2 positive, and you will find this particular complex ion. This is something very, very important. Okay, and then the next thing is that when we move down the group, the stability of these carbonates actually increases. So what I can do, I can again remove certain things. So why actually the thermal stability increases when we go down the group? Because when we go down the group, ionic nature increases, ionic character also increases. So as you can see, when we move down the group, the carbonates of your alkaline earth metals, their thermal stability increases as well as their ionic character increases. So why actually this happens? You know, your beryllium, Be2 positive, it's a very small ion, right? And this on this small region, 2 positive charge is there. Okay, so high charge is concentrated in the very small region, so its polarizing power is very high polarizing power. So what can happen in that case? Say for example you are having your carbonate ion, and when this beryllium 2 positive ion comes closer to the carbonate ion, so the electrons present on the carbonate ion will be highly polarized by the very small beryllium ion. And you know, when this polarization occurs, then covalent character increases. So basically this beryllium carbonate is having high covalent character. So what I can do, I can write here corrected, right? And now as you move down the group, the size of the metal ion increases. That means magnesium is little bigger than your beryllium, and calcium in turn is much more bigger than your beryllium, and strontium actually is again very much bigger in size when compared to the calcium, magnesium or the beryllium. So when we move down the group, the size of the metal increases, right? So due to this increased size, polarization power decreases. So your magnesium, calcium, beryllium, as we go down the group, say for example if I take the barium, so this barium is having very low polarization power. Okay, that means it cannot polarize the cloud of electron cloud of the carbonate ion pretty much, so it will have very less covalent character. That means it will have high ionic character. High ionic character. It is having very high ionic character, and you know your ionic compounds are more thermally stable than the covalent compound. That's why when we move down the group, thermal stability increases. And this is not only true for the carbonates of the alkaline earth metals, but it is also true for the nitrates of your alkaline earth metals, because they also form the nitrate. These, however, you can think in that manner that when we move down the group, ionic character increases. That means the solubility also should increase in the water, but solubility is not actually increasing down the when we move down the group for these carbonates. Solubility decreases. Why? Because hydration enthalpy or the hydration energy also decreases when we move down the group. Say your beryllium carbonate, right? It is actually decomposes somewhere around 100 degrees centigrade or less than 100 degrees centigrade. When you move for the magnesium carbonate, so it is thermally stable up to 540 degrees centigrade. Your calcium carbonate is rather more stable, up to 900 degrees centigrade. Okay, and your strontium carbonate is stable somewhere around 1290 degrees centigrade. And you know barium carbonate is exceptional. It is thermally stable up to 1360 degrees centigrade. So next is the sulfates, right? Sulfates again the very important class of the compound, and in fact you can find many applications of these sulfates, right? And again, see, water chemistry is there. Say earlier what I told you, bicarbonates and the carbonates of the alkaline earth metals which are soluble in the water, they can cause your temporary hardness. But if you have the calcium sulfate, right? Say for example, if you are having the calcium sulfate or you are having the magnesium sulfate, okay, so these are responsible for the permanent hard. That means water is said to be permanently hard if it contains your calcium sulfate or magnesium sulfate along with the chlorides also. Okay, or why it is then called the permanently hard? Because you have already seen that in case of the calcium carbonate, when you heat it, it produces lime, that is CaO, right, along with the carbon dioxide. But this reaction, right, if you have your calcium sulfate, for example, if you heat it, okay, so it will never give you your calcium oxide plus SO3. Okay, so this reaction actually is not possible. That's why this water is said to be permanently hard when the sulfates are there. This is something very, very important. And now the next thing, say for example, the sulfates of the alkaline earth metals are all white solids. See, you can check the calcium sulfate is white, okay, and your magnesium sulfate is also white, and they are also stable to the heat. That means they are thermally stable. Say for example, you are having your beryllium sulfate, okay, and the important thing about them is that the first two, they are water soluble, but as you move down the group, the solubility actually decreases. Solubility decreases. And why the solubility decreases, guys? Again, due to the lower hydration enthalpy. In fact, your barium sulfate is practically insoluble, right? It is not soluble in the water sample. However, your calcium sulfate is sparingly soluble. Okay, but you cannot dissolve your strontium sulfate, right, and your barium sulfate or your radium sulfate. They actually remain insoluble in the water. Okay, so you can see here I have also written in this particular slide, okay, the greater hydration enthalpies of these two, right, because they are having the little bit smaller size, so hydration enthalpy is quite high in that case, right, which overcomes the lattice enthalpy. That's why these two are soluble, while for all these hydration enthalpy is quite low actually, right. That's why they remains practically insoluble in that case, right. And various other compounds are also there which are very, very important industrially. Say you are having your magnesium sulfate, MgSO4 and 7H2O. So you have studied your chemistry in everyday life in your class 12. Okay, so what is this? This compound is what? This is known as Epsom salt, and this Epsom salt, because it contains the magnesium, and after the consumption it can form the magnesium hydroxide, so it's a mild laxative, which relieves the constipation. As I already told you, magnesium hydroxide is readily used in the antacids. Okay, and then you are having your next sulfate, say calcium sulfate, CaSO4. It also gets hydrated, but only half of the water molecule is there. And I hope you know what is this compound actually. Okay, what is this compound? If you remember, this is what? Plaster of Paris. Basically, this calcium is forming hemihydrate. Hemihydrate means CaSO4 dot of half H2O. Okay, and this actually, as see, the brand name of this particular hemihydrate is the plaster of Paris. And this plaster of Paris actually produced by the decomposition of your dihydrates. So if you want to synthesize this, say you are having calcium sulfate, okay, dihydrated 2H2, and if you heat it at 150 degrees centigrade, I hope you know this calcium sulfate dot 2H2O is what? It is a very important compound used in the cement industry, that is gypsum. When you heat it, then it will give you the plaster of Paris. If you further heat it, say somewhere around 200 degrees centigrade, so it will form the anhydrous salt, CaSO4. Without water, that means anhydrous. And at very high temperature, please remember, at very high temperature, somewhere around 1100 degrees centigrade, it may decompose to give you. However, in my last slide, I told you that the decomposition of calcium sulfate is not possible to give you calcium oxide and the sulfur trioxide, right? Of course, in water chemistry it is not possible, because that much of high temperature is not available in the water chemistry. But if you heat it at very high temperature of your 1100 degrees centigrade, then you can of course decompose it. Okay, please remember, it is something very, very important. And this plaster of Paris is having enormous amount of your applications, like your say if you want to plaster your walls, then you will use this one. Okay, and sometimes, you know, in the medical also, right, in the medical field also, when the person is suffering from the fracture, then that fracture actually needs to be fixed actually, and the fixing of this fracture is actually done by the plastering, and in that case where plaster of Paris is used. So these things are very, very important, which you should know. Okay, and again the same thing when you move down the group. When you if I go back, when you move down the group, thermal stability for them also increases. Okay, please remember, as I have explained for the carbonates, in that case also thermal stability increases. So I can write stability or thermal stability, both are same thing, increases. The reason is quite same. Okay, reason is quite same, because you know beryllium sulfate actually your decomposes somewhere around at 500 degrees centigrade. Okay, and this magnesium sulfate somewhere around 895 degrees centigrade. Okay, if you keep on moving, then you will have the other values also, but data is not very important. You don't need to bug out all these data, right? It would be given in the examination if needed. Okay, next are the nitrates. So nitrates also behave similarly, like all the things are same for the nitrates, as I have explained for the carbonates as well as for the sulfates. Okay, but there are certain important applications. Okay, please, you should remember. Here you can see the nitrates are made by dissolution of the carbonates in the dilute nitric acid. It's simply, if you want to prepare these nitrates, what you can take, you can dissolve these carbonate in the dilute nitric acid, then you will get your nitrates. Magnesium nitrate crystallizes with 6 water molecules. It should be noted. Okay, magnesium nitrate, MgNO3, it crystallizes with 6 water molecules. And your barium nitrate, actually it is anhydrous. Okay, so it is not having any water molecule. And these nitrates, again you can see those they show a decreasing tendency to form hydrates when we move down the group, like I have explained for the carbonates. Okay, right, because hydration enthalpy decreases. However, all these nitrates, whether your magnesium nitrate, your beryllium nitrate, okay, your calcium nitrate, whatever, right, they can produce your oxide, like I have explained for the lithium nitrate. Okay, lithium nitrate also decomposed, right? While all other nitrates do not decompose of your alkali metals, but in case of your alkaline earth metals, all the nitrates can be decomposed, right? So not barium nitrate, I am taking the example of the magnesium nitrate. Okay, say I am having my magnesium nitrate. Okay, so what I can do, I can heat this magnesium nitrate, and when I heat this, I'll produce monoxide of this one with the liberation of 4 of NO2. Okay, and you will also have the oxygen in that case. So if you want to balance this particular reaction, then what you can do, then you will take 2 of this. Okay, so this is how you can decompose them. So your alkaline earth metal, generally they form the nitrates of this kind. Okay, this kind. And but they are water soluble. Please remember, nitrates of these metals are water soluble. The solubility is there. They are water soluble. They all are water soluble. So you can see here very important feature which you should remember. Beryllium also forms this nitrate. Okay, the normal nitrate which is there. But if you actually heat this beryllium nitrate, okay, somewhere around at 125 degrees centigrade, so it forms the basic nitrate also, which is covalent in nature. Basic beryllium nitrate. Okay, so this property is only for your beryllium nitrate, while other metal ions cannot form these basic nitrates. Okay, they also form the carbides. Alkaline earth metals also form the carbides, right? Ca, C2. And then these carbides are important in the synthesis of the organic compounds. If you remember that certain hydrocarbons actually are produced by using the reaction of your sodium on the carbides. See, in class 9th and 10th, I think you have studied these reactions. Okay, so if you want to produce these carbides, how we can produce these carbides actually? Say for example, I am having my beryllium oxide. Okay, and what I can do, I can take carbon, and along with the carbon I can heat this at very high temperature, somewhere around 2000 degrees centigrade. Okay, then it result into which is the beryllium carbide. Okay, and it is red in color. Please remember, it is brick red in color. This is ionic in nature. So the very important application of this beryllium carbide is what? Okay, so what you can do, if you are having this beryllium carbide B2C, you can dissolve this into the water. Okay, and when you dissolve this into the water, it will form hydroxide of this beryllium. Okay, along with the liberation of the marsh gas or the methane gas. Okay, and to balance it, you can put 2 here, because it is forming this carbide is forming methane, so it is technically known as the methanide. So apart from this beryllium carbide, you may also actually think about your calcium carbide, which is again very important in the various applications, right? Say for example, you are having this calcium carbide. Okay, your calcium carbide is CaC2. So why this actually this compound is important? Okay, so the important thing is that when you react this compound with the nitrogen, okay, and see, of course the temperature would be very high in that case. This reaction will not happen because you know atmospheric nitrogen is quite unreactive. Okay, and if you want to react this nitrogen with this with the particular compound, then you have to heat the reaction mixture to a very high temperature. So if you heat this calcium carbide along with the nitrogen right, at a very high temperature, it will form a very important compound which is known as the CaNCN. Okay, this is very important compound, and of course your carbon would be removed from here, black carbon. Okay, or carbon black you can call it as. And this ion basically, right, say if you try to make this Ca2 positive, and then you know here this ion would be there. Since your calcium is 2 positive, you can put 2 negative over there. So this ion actually which results by the ionization of this particular compound, this is known as your cyanamide ion. This cyanamide, guys, is very important. As you can see here, it is actually consuming nitrogen. Okay, so this actually cyanamide is regularly used to actually synthesize the nitrogenous fertilizers. And this is having added advantage over the other nitrogen fertilizers, because this cyanamide actually hydrolyzes very slowly over a period of the month. Okay, so this calcium cyanamide is having extra advantages, because other nitrates, say if you are having other fertilizers, you can think of this ammonium nitrate. Okay, if your ammonium nitrate is there, so along with the ammonium nitrate you can have your urea also. Urea is more famous than the ammonium nitrate. Okay, urea. So they are also nitrogenous fertilizer, and this calcium cyanamide is also your nitrogen based fertilizer. Importance of this calcium cyanamide is that, see, it will not wash away with the rain. So generally what happens, if you put these nitrogen based fertilizers like your urea and your ammonium nitrate in your crop field, right, and suddenly say in the monsoon season, suddenly in the monsoon season, if rain occurs, then all these nitrates and the urea actually washed away with the rainwater. But this calcium cyanamide, this actually remains intact in the field. So this is having added advantage for the farmer. Okay, that's why it is important one. And there are many other industrial applications also for these calcium cyanamide. Like you can manufacture your hydrogen cyanamide. Okay, and after that, with the help of this hydrogen cyanamide, you can produce different kinds of the compound. Okay, and see, there are various reactions. However, it is not possible to cover all these things in this only one lecture. And say for example, you are having your calcium cyanamide. Now Ca and Cn, right, you are having this one. What you can do, you can dissolve this into sulfuric acid, and when you dissolve this into sulfuric acid, okay, you form this particular compound, right? And then along with this, you will also have the calcium sulfate. This you can very easily form. Okay, and this compound actually is very important. If you fix the pH of the solution, right, if you fix the pH somewhere around 9, at 9 pH, okay, so basically it will form diacyanamide. This is diacyanamide, and this diacyanamide, if you do the pyrolysis or the cracking of this one in the absence of the oxygen, pyrolysis is what? Heating in the absence of the oxygen. So it is produce a heterocyclic compound. I can write the structure of that heterocyclic compound here. So basically this is your melamine, and basically it is this is cyanuric acid. Okay, now next thing is the anomalous behavior of your beryllium. Like lithium, your beryllium is the first member of its group, right? So it is also having the anomalous behavior, and there are various kinds of the things actually which actually beryllium does, and rest of the members actually will not show those properties. So why this anomalous behavior is there? As I have explained for your alkali earth metals also, it is having very high electronegativity because it is very smallest one. See, however, in the group actually it is having higher electronegativity, right? However, it is not that electronegative when it comes to the halogens or the nitrogen, etc. Okay, but in its group actually it is small in size, so it is having the high electronegativity. And of course, its atomic radii as well as ionic radii is again very small. So due to this actually it shows the various different properties, right? It is also having the very high ionization energy. So due to the high ionization energy, smaller size, high electronegativity, it actually behaves distinctly from the rest of the members of the group. Okay, so what are those actually? You can see here, beryllium is hard metal, while other alkaline earth metals are soft actually. Okay, So beryllium, in that case, it is least metallic in nature and it forms the covalent compound. You have already seen few examples of this. Okay, like I have explained for the beryllium carbonate, beryllium nitrate. Okay, and this is easily hydrolyzed. You know, it forms the tetrahydrated ion. So it is important to keep the beryllium carbonate in the atmosphere of the carbon dioxide. Otherwise, it is formed your hydrated ion, not simple Be2 positive, but it will form the BeH2O4 2 positive. Okay, its melting point, boiling point, ionization enthalpy is highest among all the other among the group actually, while rest of the metals actually are having a low melting, boiling and ionization enthalpy in comparison to the beryllium. Okay, and in case of the oxides and the hydroxide, I know I actually already told you this actually your amphoteric in nature. Okay, while other hydroxides and oxides, they are basic in nature. Beryllium will not liberate any kind of the hydrogen when you put the beryllium into the HCl or H2SO4, but other alkaline earth metals, when you put in the acid, actually they produce hydrogen. So I forgot to put this particular reaction, but I can give you the example. Say for example, you are having calcium and you put this calcium into the HCl. So what will happen? You will have the calcium chloride along with the hydrogen. So it can liberate hydrogen. Okay. So if you want to balance this reaction, you can take 2 moles of this. However, this reaction is not possible when you do the same reaction with the beryllium. Okay, and your beryllium does not show coordination a number more than 4, right? Okay, more than 4 actually, right? Coordination number is more than 4. Just say for example, you have already seen this 2 positive. Okay, so this coordination number is only 4 in that case. Okay, so this 4 actually is not here. So if I want to correct it, so what I can do, I can remove this from here and I can put my 4 here. Okay, and why this happens? Because d orbitals are absent in that case, so it cannot accommodate other ligands around itself. Okay, so that's why it is show only the 4 coordination number. Like your say beryllium has very strong tendency to form the complex compounds, as you can see here in that case, while others are not very keen to form the complexes. Okay, and in the flame color, right, I already explained to you that beryllium is not actually show, beryllium does not show any important color in the flame. And beryllium sulfate is if you have the beryllium sulfate, right, BeSO4, it is water soluble, while the solubility decreases when we move down the group. So all these things actually I have explained. There should be something which must be there in the lecture, that is the diagonal relationship. Okay, you know, it happens this diagonal relationship actually happens in case of the second and the third period of the compound. Okay, so what you can do, say you are having beryllium, okay, and you are having your magnesium, you can write in that manner, and you are having boron. After that you are having boron, and this is you are having aluminium. Basically it is group 2, no, and it is your group 3. Okay, and you know this is your second period and this is your third period, and this beryllium is diagonally placed with respect to the aluminium in the periodic table. So they actually are having similar properties, but there should be a certain reason behind this. So see, I am not writing everything on the slide. What you can do, you can listen carefully and make your own notes by pausing the video if you want. Otherwise textbooks are there to explain all these things. Okay, so both, whether you are beryllium ion or your aluminium ion, right, say you are having beryllium ion Be2 positive and you are having your aluminium ion Al3 positive, right. So if you compare these two ions, right, so they both are having very high polarization power, and again their electronegativity are also same, not exact value but approximately same, and their reduction potential is also same. So all these things actually makes them similar towards the various kinds of the reagents, and they show the various kinds of the similar properties. Okay, you know your aluminium oxide, your aluminium is prone to oxidation, further oxidation. Why? Because it's from the Al2O3. And if you know the Pilling-Bedworth rule, Pilling-Bedworth rule we generally study in the corrosion chemistry, right? So what the Pilling-Bedworth rule says that when the oxidation of the particular metal occur and the oxide is formed, like I have formed this aluminium oxide, right? So it's a protective coating. It actually covers the surface of the aluminium, fresh aluminium completely, and the penetration of the fresh oxygen will not occur because the surface area is very high for this one. So it is corrosion resistance. In the same way, your beryllium also resistant to the oxidation, or say the corrosion. So they are actually, they both are unaffected, like the beryllium as well as your aluminium, both are unaffected by the atmosphere. The decomposition of the beryllium actually would not occur in the water, and this is also true for the aluminium. And if you want to know some other reaction, right, say for example you are having beryllium metal and you try to dissolve this beryllium into the sodium hydroxide, so it will form a compound, a kind of a salt with sodium with the liberation of the hydrogen. That means from the alkaline solution, right, beryllium can liberate hydrogen. And same reaction, say if you are having your aluminium, okay, and you are reacting this aluminium with the sodium hydroxide, of course your water is needed here in that case, okay, so it will also form the same kind of the salt, 2Na-AlO2, sodium meta aluminate with the liberation of the hydrogen. So aluminium can also liberate hydrogen. So if you want to balance the reaction, you can various other reactions are also there. Say for example, if you are having beryllium oxide, right, and if you dissolve this beryllium hydroxide into sulfuric acid, so it will form the beryllium sulfate, BeSO4, along with the water. So this must be true for the aluminium also. Okay, now say suppose I am having my aluminium oxide, which is alumina, Al2O3, and I put this alumina into the HCl. Okay, so it will form AlCl3, aluminium chloride, and of course water molecules would be there. If you want to balance this reaction, you can do easily, right? 2 of this is required, that means 6 of HCl would be there, okay, then 6, that means 3 of H2O would be there. So in this way you can balance the reaction also. Say for example you are having your beryllium hydroxide, BeOH whole twice. If you react this with the HCl, okay, it will form your halide, BeCl2, in the water, and it is insoluble. Please remember, this is insoluble. Likewise, you can take your aluminium hydroxide and you can put this aluminium hydroxide into HCl. Of course 3 of HCl would require in that case. However, if you heat them, these hydroxide, if you heat them, then you can decompose them, okay. And see, aluminium also form the polymeric compound, beryllium also form the polymeric compound. Basically polymeric hydrides they form actually. And say if you are having your beryllium, it can combine with the nitrogen and it will form the beryllium nitride. The same reaction is also shown by the aluminium also. So you can write 2 of Aln, aluminium nitride. So in this way they show the diagonal relationship. Group 2 elements are also important, and among those, calcium is very important. Basically 23 essential elements are required for the human body, and out of these 15 comes from the S block elements. You know, sodium from the S block elements, potassium from the S block elements. Now the calcium, you know, half of the world, please remember this thing, half of the population of the world is suffering from the deficiency of the calcium, right? And this is the reason for the weak bones, right? And see, if you want to know the biochemistry or the bioinorganic chemistry, if you want to learn, then, or if you try to learn, then you will understand that when you have the deficiency of the calcium in your body, then definitely you will also have the deficiency of the iron, because the absorption of the iron takes place in the presence of the calcium. So if the body is calcium deficient, then you will also anemic. That means iron deficiency would also be there. This is the reason in the Ayurveda they mention the betel, pan. You know, this pan we already know. Lots of people are very fond of this pan, and this is mentioned in the pan is basically betel, right? Betel leaf. Okay, and this is mentioned in the Ayurveda also. If you put some of the lime over there, right? Chuna, which you used along with your surti or some tobacco, right? This is very very important, lime, and this needs to be there in your diet also. See, what we people do actually, we take the very very expensive and costly supplements to actually overcome the problem of the calcium. However, I think there is no need to go for those expensive supplements. You take little of lime actually, right? And you put on this here on the betel leaf and consume it regularly. And you can put a pinch of this tuna into your dal, or you can make a mixture of a little, say a pinch of this calcium carbonate into the water, and try to dissolve it. Whatever the amount will dissolve, filter it and drink the water. So it will actually it will be more helpful or more beneficial than the expensive your calcium supplements. And after that, your magnesium is very very important. Okay, and you know this magnesium is very important component of your chlorophyll, right? If magnesium is not there in the chlorophyll, then you will not have the process of the photosynthesis, right? So there are various important things which you need to understand about these elements. However, it is not possible for me to include all the things in the literature in the one or two lectures. You actually, if you are interested in learning all these things, then you can learn by your own also. Basically, you see, 90 gram sodium is there in the human body, 5 gram potassium is there, okay, magnesium 25 gram, calcium is 1200 gram, okay, 1200 to 1400, it varies according to the age. Okay, all these things are there. So I hope I have covered all the important things of about your alkali metals are in this particular lecture, alkaline earth metals. Okay, and in the next lecture I will meet you with the question answers, right? So how we can approach to solve the questions based on these things. Okay, so that's it for today. And if you are new here watching video for the first time, please subscribe the tetrahedron chemistry classes and do share with your friends also. So so that's it for today. So thank you very much. Thanks for watching.